Good morning, everyone. Welcome to day 3 of this online joint faculty development program on designing with FPGAs. Good morning, Padmanabhan sir and dear participants.
Good morning, Biplav. Should we start?
So the first topic for today is Introduction to HLS and Intel HLS compiler by Padmanabhan sir. Padmanabhan sir, I am making it a presenter.
Thank you so much for the warm welcome.
Over to you, sir.
Yeah, thank you so much. Yeah, let me start the presentation. Hope you are able to see my screen.
Visible, sir.
Thank you so much. Good morning, everyone. Welcome to the day 3 of the faculty development program. On day 1, we discussed on the introduction to Intel FPGAs and Quartus Prime design software. And yesterday we focused on the timing analysis and how to apply timing constraints and achieving the timing closure along with the clock domain crossing techniques. Today our focus would be on the high-level synthesis with Intel FPGAs. So let us understand the objectives. So what is the objective of this session? We are going to understand the concept of high-level synthesis for Intel FPGAs. Use the Intel HLS compiler to synthesize, functionally verify, and simulate design IP for Intel FPGA. We are going to understand how the component executes on the FPGA. We can take that to the Quartus or to the platform designer, and how do we integrate the system? That's what we are going to learn later. Let us explore, why do we need to have high-level synthesis? That's the question everyone will have. Because for the first 2 days, like we were discussing on Verilog and VHDL, we all knew that the HDL, the hardware description languages, are concurrent in nature. And we all have also seen that there are 3 major characteristics of HDL. One is we can perform simulation. Number 2, synthesis. And also we can perform design reuse, which is called as documentation. So when we say simulation, we can verify the functionality of the design by passing suitable test vectors. We have also translated the code, the HDL code, into an equivalent gate level schematic. When we were discussing about the Quartus Prime design software, we have seen the RTL schematic, which is the technology independent schematic. And we have also seen the technology mapped schematic after synthesis and the fitter process, that is the placement and routing process. Then why do we need to learn high-level synthesis, right? So we discussed more about Verilog and VHDL and what are the different characteristics of HDL and how do we synthesize the design, how do we take it and perform placement and routing. We generate the SRAM object file and we implemented the design onto the FPGA using the physical board. Also, we tried with a remote lab setup of LabSlant. Right, now let us understand what is the need for high-level synthesis. Verilog or VHDL or hardware description languages, they are not algorithmic in nature. So what we are trying to do using C++ instead of RTL as the primary design entry language enables engineers to focus on algorithm level optimization and less on time consuming hardware level optimization. So what is the basic idea here is we are going to use the high level languages like C or C++, and we are going to convert that code into an RTL. That's the base idea. So we require a tool which converts the C or C++ code into an RTL. So designers can then execute the FPGA component as a C++ program on a CPU. Now the C++ level execution enables verification that is orders of magnitude faster than RTL simulators. Now you can see that it is faster than the RTL simulator because the simulators we have seen, like the Intel FPGA Starter Edition simulator, which we are using for performing the RTL simulation. Right now, the greatest advantage is the C++ level execution enables verification that is orders of magnitude faster than the RTL simulators. And then what is this high-level synthesis? That's what we wanted to know. We use an Intel HLS compiler, which is a high-level synthesis compiler, which takes the C or C++ code as an input and converts that into Verilog or VHDL. That means you can take that to an Intel Quartus Prime design software generate binary and implement the design onto the board. It can be targeted for Cyclone or Stratix or Aria or Agilex or any device. In our lab, we are going to target it for the Max 10 device, right? So any device we can target it. So what are the greatest advantages, right? What are the best features we have? The first one is it is ease of use, and it is providing FPGA quality of results. The FPGA quality of results, when you say, it is going to show that what kind of FPGA resources are used by the design. That means you are going to see how many number of the lookup tables. In our case, it is called as adaptive logic modules, ALMs, or ALUTs, right? Where adaptive lookup tables, where you can use this for different set of variations. Also, we can see that what kind of memory resources that are used and what kind of DSP resources that are used by the design. Everything we can see that, so that we can see the FPGA quality of results. As we knew that there are 5 important resources inside the FPGA. The one is called as the basic resources, which includes our lookup table and adaptive logic module. Then on-chip memory, which is the memory resources. Then we have a dedicated multiplier and accumulate unit, which is the DSP resources. We also have the clocking resources, which is the PLL, right? In Max 10 device, we have 4 PLLs. So that is the PLL device. And then we also have IO resources. How many IO pins are there? So we would be getting the FPGA quality of results, and we can also see the partnerships and ecosystem. We have different partnerships and ecosystems that could be possible with the Intel HLS compiler. So let me just walk you through our Intel HLS compiler page to get more details. Okay. So the moment you type Intel HLS compiler, it will take to our page where you can get more information about our Intel high-level synthesis compiler. So the Intel high-level synthesis compiler is a high-level synthesis tool that takes in untimed C++ as an input and generates production quality register transfer level RTL code that is optimized for Intel FPGAs. You can see that. And as I mentioned, you can see the models developed in C++ are typically verified orders of magnitude faster than RTL. And we can also see the Intel HLS compiler is included in the Intel Quartus Prime design software installation. We don't want to install it separately, but we need to install the GCC compiler, and how that could be installed. All the steps would be explained to you during the lab session. Right, so this particular page will have more details about what are the features of the high-level synthesis compiler and the getting started guide, and then the documentation and support. And then you can also register for the instructor-led training course, and also there is an online training that is available for the Intel high-level synthesis compiler. There are 7 parts of the training. I request you to go through all the trainings that will give it an idea of about high-level synthesis in detail. Right, let us again go back to the session. So there are multiple flows, and we are going to integrate that to the IP, that is the intellectual property, into the system. So you take a C or C++ code, and then we use an Intel high-level synthesis compiler. And from there, we can directly perform different types of integration flow. So the direct HDL instantiation, we can instantiate the IP as a component into our Quartus Prime design software, or we can use the platform designer, which we will discuss in detail in the afternoon session. And then we can also see in the first day, right, when Anil Sama introduced about in the keynote about the programmable acceleration cards, right? We have different programmable acceleration cards, like from the ARIA pack card as well as the Statix 10 D5005. We have different programmable acceleration cards that are useful as an FPGA accelerators. We will get more details about that on the Thursday session. And you have Intel FPGA SDK for OpenCL. And also we have Intel One API that could be targeted for XPUs. It could be targeted for CPUs, GPUs, right, AIPUs, as well as for FPGAs. That's what we call that as a One API, which is called as the cross-architecture performance. So the main question, whenever we learn a concept, what is very important for us is like what kind of applications that particular tool is used. The main question what comes up in our mind is like why, then how. These are the two words we will ask, right? First question is why. Why do we need to learn it? Then how do we approach it is something later. Now the question is why. why do we need to learn high-level synthesis compiler, or why HLS? When we say what kind of markets it takes care of, let us go through that. The first one is the algorithmic market, where you have AI as well as ML, machine learning. We will get more details about the AI and machine learning in tomorrow's session. And also you can see about high performance computing, industrial, vision sensor, motor control, and smart city and IoT applications, automotive ADAS applications, and the military, as well as wireless and 5G applications. In all these applications, we can use Intel high-level synthesis compiler, which is the greatest set of applications which we can target for. What is the agenda? Let us get into the details here. So we need to understand about the introduction. We have seen that. Now let us go through the X86 emulation, and then the co-simulation, and then the analysis of reports. I will just explain the theoretical concept of how those reports would be generated and what would be present in those reports. Later you can see the demonstration of the Intel high-level synthesis compiler in detail. So at this junction, you would have got some overall idea, like what could be the features of the high-level synthesis tool. So using the high-level synthesis tool, you may get an idea right now that we can synthesize a C or C++ function into an RTL implementation, and we can develop that component in a software environment and functionally verify that component within a software environment and seamlessly integrate with hardware simulation environment, optimize the design using the software-centric tools and reports, and we can also integrate the generated IP easily within the traditional FPGA design tools. It can be a Qualtus design software as well as the platform design. Right, so this slide gives you an overall picture. As you are aware that we have the Agilex, which is our 10 nanometer device, and then you can see Stratix, our 14 nanometer, and then ARIA, our 20 nanometer, which is our mid-range device, as well as you can see the low-end devices, Max 10 and Cyclone 5. So what is the basic idea? Like, why do we need to use this high-level synthesis, and what do we need to use it for the FPGA algorithms? Let us understand that. Because we know the characteristics of FPGA, that it is flexible, it is multifunctional, reprogrammable silicon, and we have the custom hardware functionality, and it is a bare metal speed and reliability, and it is truly parallel in nature. So that's what we have used the HDLs like Verilog and VHDL, because they are concurrent in nature. Now, not only the set of markets which we have seen in the earlier discussion, there are multiple markets that are emerging in the FPGA field also. We have seen the applications where we can use the Intel high-level synthesis compiler. Now you can see that different set of markets are available for the FPGA also. Now, how we are going to integrate them together? Let us explore that in detail right now. Let us see the traditional flow, what we discussed in the first 2 days. We have developed the RTL code. We performed analysis and elaboration, and we did perform functional simulation using the Model Sim Intel FPGA Starter Edition tool. We performed synthesis, and then we performed filter operation, placement, and routing. We generated the assembler file, which is we generated the SRAM object file. We implemented the design onto the code. Along with that, we also performed timing analysis yesterday in detail and understood that why the design is having setup violations and how to overcome setup and hold violations, and what are the multiple clock domain techniques that need to be adopted, and what are timing exceptions, and we fixed the false path, multi-cycle paths, pure combinational logic paths, everything. But now this is the traditional Qualtus tool flow, what we follow. Now, what is the drawback, and why do we need to fit into the high-level synthesis compiler in this case? Let us get into the detail. The traditional FPGA design process, which we discussed in the earlier slide, is a potentially time-consuming effort. Why? We started the design with developing the HDL. We performed behavioral simulation. Then we performed synthesis. Then we performed placement and routing. We applied timing constraints, synopsis design constraints, We applied the basic constraints as well as we applied the complex timing constraints, and then we should achieve the timing closure. After achieving the timing closure, we should implement the design onto the board, let us assume. So definitely it is a time consuming process for us because we have to go through all these steps, right? So developing the HDL for an algorithm definitely would be time consuming for us. Then we need to perform behavioral simulation. In that case, we need to pass all the test cases that are required to ensure that the design is providing the intended functionality. That is one more challenge what we have. The third one, what is very important is when we develop the HDL, whether it provides the correct hardware or not, what is required. For example, in some cases, it may not provide the correct hardware what we require. In that case, we need to apply different set of techniques. We need to apply some synthesis attributes. We need to perform different optimization techniques in order to ensure that we should get the correct hardware, and then we should perform area optimization. Then we should think, okay, how to do timing optimization. We should know power optimization. And sometimes your design may not meet timing. You will have setup violation or hold violation, or both violations can be present in the same design. We need to fix them with different techniques. So in all these places, you can see there are multiple places where we need to understand that the stages are time consuming. That is the traditional FPGA design process which we followed, and which we are following right now. Now, what we are going to do at this junction, when you say we are going to raise the design abstraction from RTL to C++. In our case, what we are going to do is we are going to generate the RTL in the Intel high-level synthesis compiler, and we can verify the RTL with the test bench core simulation with the Model Sim Intel FPGA Start Edition tool. And not only that, we can review the reports, and we can see the performance, utilization, and we can also view the bottlenecks, right? What is the kind of problems we are facing in the design? All the informations we will come to. So there are different set of optimization techniques that could be followed, which helps you to optimize the performance, where we can modify the C++ component, and we can re-verify the C++ test bench, and also we can review the reports, okay, which provides you the exact performance what we wanted. And main important thing is the utilization. What kind of resources it utilizes, that is very important for us. And sometimes we need to view the bottlenecks, because that will give you an idea that, okay, what kind of other optimization techniques that could be adopted for this design so that we can get a efficient design. So now you can see that debugging software is much faster than hardware. So that's what we understood from the discussions what we had. And it is very clear that it is very easier for us to specify the functions in software. So simulation of RTL take 1,000 times longer than the software. So in order to see that, okay, so all these drawbacks, what we can see that from the RTL side, how that could be adopted and how it is made very easy for us in the high-level synthesis or on the software side. That's what is our discussion. So since we can see that it is very easier to specify the functions in the software, and also we can see the simulation of the RTL take 1,000 times longer than the software. So the hardware takes more time than the software. So then in that case, there would be a higher level of abstraction. And also we should see that, okay, whether it is giving you high productivity or not. That's what we need to get into the details. To achieve that, what is the kind of step, or what are the steps that we are going to follow in the Intel high-level synthesis compiler is the slide what we are discussing now. In the HLS use case model, we have a C or C++ code where we have multiple functions, and we use a standard GCC or G++ compiler and convert that into an executable file. If you see on the right-hand side, there is a source file, which is a C or a C++ file, and then you have a corresponding header file library. And we feed that to the G++ or a GCC compiler, which is a standard file, and then we get the executable file for it. What is the difference here? That's what we are going to see. Now we take those directives and take it to the Intel HLS compiler, convert it into an HDL IP, the intellectual property, and then we can integrate that to the Intel Quartus software ecosystem where we can integrate that with the platform design. So all the facilities are available here. So we need to use some HLS directives, and with the HLS compiler, you will get an IP that is an HDL IP. So the RTL would be available. It can be also available as an IP, which could be integrated with the platform designer system integration tool. Right. So what is the basic idea right now? What did we arrive at right now? The Intel high-level synthesis compiler is targeted for Intel FPGAs. And what is the command line executable we are going to use is called I++. And now we are going to integrate that into a traditional FPGA design using the FPGA tools. So what we are going to do in this step is, like, we have a C or C++ code that is fed to the Intel HLS compiler, then convert it as an IP, and you can take it to the Intel Quartus Prime design software, or we can take that to the platform design. And what is very important for us is how we are going to achieve this goal, right? So it is very easy for us to convert a code into an RTL, let us assume. Then what is very important in the hardware is, like, we wanted to perform different optimization techniques. That means you should ensure that the design should take less area, right? It should operate at a higher frequency. We want the higher performance. Now, what is the kind of goal? What we wanted here is, we wanted the same performance as hand-coded RTL. How do we develop the code? In the similar way, we wanted to achieve the performance, but there can be, or there could be, an increase of about 10 to 15% resources. So what is the kind of resource that would be taken when we do a hand-coded RTL? When compared to that, it can take more than, right, 10 to 15% of that. But what we wanted at the end of the day is, like, we should achieve, or we should get the same performance. Is that applicable? Is that possible? That is the kind of logic which we are going to discuss in detail. What are the requirements of the Intel high-level synthesis compiler? If you go through the requirements, you require the Intel Quartus Prime design software. We all have installed it and it is ready. And we have the model simulator, which is the Intel FPGA Starter Edition, that is also available. Only thing what we need to install is the Visual Studio. We need to install Visual Studio for C++ 2010 version, which we will tell you how that could be installed. And we have appropriate licenses for all the tools. So since we are going to use the Intel Quartus Prime Lite Edition, we don't require the license for any of these tools. And Intel HLS compiler is integrated in the Intel Quartus Prime design software. You don't require any specific license required for performing the high-level synthesis. Now, what is very important here is, there is also an Intel high-level synthesis compiler getting started guide that is available, which provides you more use. Right. If there's any question in the chat, can you please help me out?
I don't see so far any questions.
All right. Okay, please. I will also take it. Thank you. Thanks. So in the HLS procedure, we have to create the component, and we should see the test bench in C++. What we are going to use is the emulation process. Use MARC, which is the microprocessor architecture, which is X86-64. Then we are going to generate the IP. Then we are going to examine the compiler generated reports, and we run Intel Quartus Prime software compile on the generated IP. And then we are going to generate the quality of results, and we integrate the IP with the rest of our FPGA system. So now if you look at on the left hand side, we have a C or C++ code, and then we have an Intel high level synthesis compiler, and then that could be integrated as an HDL IP. Right, what are the steps here? Let us go through here. We need to develop with C or C++. What is the command that need to be followed? I++ -mark is equal to x86 -64, and then we see what is the C or C++ code. So this is with develop with C or C++. When we do the same with the high level synthesis, what is very important here is that I++-mark is equal to FPGA family. It can be Max10, or it can be Cyclone 5, or it can be ARIA10, or Stratix or Agilex. We need to provide the component, which is the function, and then it provides you the source value. What are the kind of outputs or what folders would be created when we perform the compiler for high-level synthesis? You have an executable which will run calls in function and simulation of the synthesized IP. And we also have a project components, all the necessary files to include IP in the Intel Quartus project. .qsys file, this is for the platform designer. .ip file, which is the Quartus IP file, and .v file, where we can directly instantiate that into the Quartus Prime Design software. We also have the reports file, where we have the component hardware implementation reports. We have a verification folder where the simulation test bench would be available. And we also have a Quartus folder where we have the Quartus project to compile all the intellectual properties. Generally, it starts with A dot. That means A is the default output name. And -o option when we provide, that could be used to specify a non-default output name. That could also be possible. So in our case, that we can see there are different set of projects that are performed after the simulation step. So let me walk you through that, and then we will come back to the presentation. If you go through this, you can see there is a co-simulation.prg file where you can get all the reports that are available there. As I mentioned in the presentation, you can see components folder, you see Quartus, we see reports, as well as the verification folder. As it is mentioned in the presentation, when we open the components folder, you can see a set of instantiation. You can see there is an instantiation file which produces you the instantiation template. So this instantiation template, we can directly use it. So we can see the instantiation template that could be integrated in the top level module. And we can use this into our Quartus project, and we can instantiate this intellectual property. Also, you have a square root.qsys file, which is the Quartus system integration file that could be directly integrated into the platform designer, which we will discuss in detail later. Now, if we open the next set of components like Quartus, where we can see there is a Quartus project file that is available, which is a QPF that is available. And also you have a QSF file, which is the Quartus setting file. And then you can also see a generate report TCL file, which shows that how the reports can be generated. And also there is a reports tab where you can see the report.html file, which you could see the details of all the HTML reports that could be generated. So you can see that it shows that what are the different set of adaptive logic modules, like I told you, adaptive lookup tables, right? And how many number of flip-flops are used, and how many RAMs are used, and how many digital signal processing blocks, DSPs, are used. All these details could be seen now. So it is very important for us is that the code, when it is getting converted into an RTL, we could see what is the estimated resource usage. That information could be seen here. And on the summary tab, when we click this, you can see that what kind of loop analysis are there, which you will discuss in detail later. All this information could be seen in the report itself. And you can also see the area analysis of system. That means you can see that in the system, how many resources it has taken. And when we expand that, you can see that, okay, in each and every component, that means a subblock, subsystem, what kind of resources are used, you can see that. In the blocks, you can see that what kind of resources are used on the adaptive lookup table side, flip-flop side, RAM side, and DSP side. All these informations could be seen on the report side. Not only that, what could also be seen is like we can also see the different set of component where you can see the loops analysis, right? Each and every loop, right? You can see the kind of clock cycles, what it is taken, which is critical. Everything could also be noted down in the high-level synthesis compiler. You can see the initiation interval, which shows that how many number of clock cycles are taken and why it is taking, because it shows that there is a data dependency, and all this information will also be seen, which we'll discuss in detail later. Just to show you that what are the capabilities. Now you can see the code is getting converted into an RTL, and you can see the multiple folders which it generates the reports, and then we can see that in the HTML file. And then we have a verification folder where you have the details related to the test bench, where you can see how we can simulate the design using the models Intel FPGA starter edition. And you can see there is a test bench folder where all the information and the test bench generation reports are available. So these are the four important folders which the tool will generate. That's what I explained and showed to you. So that was showing here. As I mentioned that here in the components folder, you have all the files which are necessary to include the IP in the Intel Quartus Prime Design software project. And in the reports folder, you will have component hardware implementation reports. And in the verification folder, we will have simulation test bench. And we will have a Quartus project where you can compile all the intellectual property. Now let us move on to the X86 emulation, like what is the kind of command that we are going to use for performing X86 emulation. You can see -mark is equal to X86 -64, which is 64-bit. And what is the necessity of that? Let us see that. When we need to do core simulation, what happens in the core simulation process is it generates the intellectual property, and it also examines the compiler generated reports. The compiler generated reports, we have seen that. Now what kind of reports it is generated. We can see what kind of resources that has been taken from the FPGA we have seen, like what are the number of adaptive logic modules like A lookup tables, the kind of memory resources it has taken, the kind of DSP resources it has taken, the kind of registers, the ALM registers it has taken. All this information we can see that. Now, why do we need to do core simulation? And what is the necessity, and how that would communication can get performed? Let us understand that. In the core simulation process, it combines the x86 test bench with the RTL simulation. So we have an HDL code for the components which runs in the RTL simulator, which is Verilog. The RTL test bench automatically created from the software. So you can see that what is the greatest advantage is you have the RTL test bench, which is automatically created from the software. Because when we were developing for the first 2 days, we were developing the test bench to verify the memory component, to verify a specific hardware. But now the greatest advantage is the RTL test bench would be automatically created from the software. And one more important thing, what we also need to understand, appreciate is when we were using the Verilog HDL, we were using the programming language interface, which is a PLI, where we need to communicate between any languages like C or C++. We use a programming language interface. What is the challenge with Verilog to do with the PLI was the Verilog does not have like the 2-state and 4-state data types like what system Verilog has. Most of the data types which are available in system Verilog are taken from C and C++, where we have int, you have short int, you have long int, you have bit, you have byte, all those data types which are available in C and C++ that is available in system Verilog. Also, we have struct and union which are available in C and C++. Therefore, it is very easy to perform the C and C++ interaction with respect to system Verilog. And we call that communication as a direct programming interface, which is called as DPI. So the communication using system Verilog would be performed using the direct programming interface, which is DPI. So which allows the C and C++ to interface with system Verilog. Interprocess communication library used to pass test bench input data to RTL simulator and returns the data back to the x86 test bench. Now I explained to you that what are the specific folders that are generated when you perform the high-level synthesis component. What is very important to understand here in the core simulation flow It's like we need to provide the FPGA family because it depends on the FPGA family which we are targeting for. So we have seen the details of the information related to the hardware, where what kind of adaptive logic modules and then what kind of resources it has taken. What is very important for us to note down is the co-simulation verifying the high-level synthesis IP. So the Intel HLS compiler automatically compiles and links C++ test bench with an instance of the component running in an RTL simulator. Now in this case, in order to verify the RTL behavior of the IP, we need to run the executable generated by the HLS compiler targeting the FPGA architecture. So in that case, what is important is what we have seen earlier is like we need to target it for the corresponding FPGA family. And when we go through the verification project, we can take it to the module sim and verify the functionality also. Let us understand the simulation framework. In the C++ test bench process, we use the user test bench, we run main, we send component inputs, we run the component, and we wait for the component to finish and retrieve the output. But then here in the model sim simulator process, we are going to run the RTL's test bench, and then we do bus functional modeling interfaces. We generate the components and then we do the IPC, inter-process communication. So that would be the basic simulation framework that we do in the Intel high-level synthesis process. What are the 3 steps which we are going to do in our lab, and what is our main component that need to be addressed in the high-level synthesis compiler is we compile and verify on X86, we iterate on the algorithm, we perform functional verification. We debug using BDP or Valgrind that would be used for any specific advanced operations like pointers, right? That could be used. And we need to compile for FPGA, where we need to examine the FPGA reports, iterate on the architecture of the design, and we use the reports as feedback and understand what are the bottlenecks. Finally, we need to simulate using the model sim simulator. We test the functionality. We also test latency and performance during different set of verification tests. Right, so we didn't achieve what we wanted. We have performed, the code is getting converted into an RTL, but what we expected and what we are getting is something different. That means we are going to see what is the fundamental difference between RTL versus HLS later. But now, what are the very important things that we need to look into is, there are chances where you would have used improper use of HLS compiler directives, improper use of HLS compiler attributes, and improper use of HLS specific constructs. So when we refer into the Intel HLS guide, we can find out that what are the different high-level synthesis compiler directives that need to be used, kind of pragmas that need to be used, that would be addressed in detail. We can also see the high-level synthesis compiler attributes, and we could also see how we need to use the HLS specific constructs. Sometimes the improper usage of the high-level synthesis compiler directives or the attributes or specific constructs, right, may not give you the exact behavior. What we wanted and what we are observing may be something different. So it is very critical and important, and it is essential that we need to go through how do we use the high-level synthesis compiler directives, and how do we use their attributes, and how do we use the specific construct so that it is going to provide us the corresponding hardware. Now, we need to perform co-simulation because that is very important for us to ensure before integrating that to the FPGA component, we should know that what resources are taken by the two. What are the 2 important commands? The first one is the I++ -mmark is equal to x86-64. We are going to provide my file, that is your C++ file, -o. So if you are not providing -o, then it would be by default, it will take A dot. So that information could be taken into account. Exactly. There are chances that we may need to target it for a specific FPGA family, as I mentioned. I++ hyphen MR is equal to FPGA family. If you see here, FPGA only. So it is creating the FPGA component project, RTL and co-simulation support, and then it generates the logic of notice bench binary. What is very important here is we can compile the resulting HDL files using the Intel Quartus Prime design software. And one more important option what we have, we can optimize the RTL for the specified clock frequency or period. We can specify the clock. That means you can see it is specified that we can optimize the design for 400 megahertz. And there are multiple options that are available, which is present in the Intel HLS compiler reference band, which we will discuss in detail later. Now, how do you debug? When you say we have to debug the visibility, so what is the syntax we follow is to get full debug visibility and logging of on signals, we use the HDL. You can see GHDL. This is the option which we use for performing the co-simulation. Let me spend some time in showing the reports. I showed you the reports like how it will get generated, but in the next section, we can see step by step how those reports are generated and what would be available in each and every report. So the Intel high-level synthesis compiler automatically generates an HTML report that analyzes various aspects of your function, including area, loop structure, memory usage, and system data flow. Where it is located at a.prg reports and report.html. There are multiple reports that are available. Many types of reports are available. When I opened that reports tab, I showed you that you can see the summary, loop analysis, area analysis of system, area analysis of source, component viewer, component memory viewer, verification statistics. There are multiple tabs that are opened in the report. We can get the idea of that what are the kind of loop analysis, because your code will have more number of blocks, right? Which block is starting and which block is ending, then we need to have multiple loops, because while writing the HDL code, we will give less importance for the loops. But then when you are trying to write the code in terms of the high level language, we need to write the algorithm in terms of loops. So when there is a loop analysis, then it is very critical and important for us to understand how many clock cycles that loop takes. That is very important, so that we can think of different optimization techniques that could be followed by that. So we need to understand the loop analysis. We need to see the area analysis of system and the area analysis of source, where we can see in each and every block what kind of resources it has taken, that we can get into the detail, and we can see the component, and then any memory viewer, any memory that has been taken, and we can shoot the verification statistics also. This is the report I showed you. You can see that it shows the overall FPGA resource utilization, which is important. You can see the adaptive logic module, ALM. Right. So get a recap. Just understand that you have a lookup table, which is a 4-input lookup table that was traditionally there. Now we have an 8-input lookup table inside the ALM. You have the adders and then registers. Right. Now, what is also very important is using this adaptive logic module. Right, we will build the logic array block, which is called as an LAB, and using that logic array block, we will build a memory, which is called as a memory logic array block, which is called as a distributed memory. That means along with the on-chip memory, you also have the memory that is built using the logic array block. So you can see here in the Quartus fit resource utilization summary, you can see the frequency of the clock, what is the frequency of operation. And you can see that it shows that how many resources are taken, like ALMs, flip-flops, RAMs, and DSPs. And we can see the estimated resource usage, how much it has taken, what is the percentage. That information we can see. Because you can see how many are available in the device, and that how many are used, that we can see the percentage. This is very important for us to check whether do we need to optimize still further, or is the area is correct, or is the area is very high, then we can take a call. Sometimes the code will use more number of memory resources, and sometimes the code will use more number of DSP resources, right? We have to see that how many number of DSP blocks are available, resources are available, and how many are used by the design, we can see. Right, and it also depends on the kind of FPGA what we use, because when we target it for the corresponding FPGA family, we have to see that what kind of memory resources and DSP resources are available in that device, right? It is going to optimize for that device. So we can see three important things here. One is the FPGA resource utilization. The second one is the compile warnings. If there are any warnings that is generated by the tool, that we can see in detail. And the Intel Quartus software fit results. That means after performing placement and routing, we can see that what is the resource utilization summary. So you can see here Quartus fit resource utilization summary. So this is called as the summary tab, which is very important for us to look into. The second thing is on the loops. As I was explaining to you, there is a problem with respect to the loops. So you can see the loop analysis report to see if and how each loop is optimized. There are chances that the loop would be unrolled. That means it is fully unrolled or it is partially unrolled. Whether you wanted to reach the limit, because we are going to specify what is the limit of that loop. Whether it has reached that or not, we can check it. And whether the design has been pipelined. You can see that in the initiation interval, it has shown that how many number of clock cycles are taken for each and every block. And what is the problem of that? What is the bottleneck? It showed there is a data dependency. Because you wanted to do load and store operations, or you wanted to do a storage operation, we have to see that, okay, whether it has been pipelined or not. So in one case, we can take that whether you wanted to use an on-chip memory or we wanted to use an external memory. Let us think that, okay, when it is an on-chip memory, what is the basic advantage we get is like it is faster. All the things can happen in one cycle. That is not the case when we try to use an external memory, because it will take more than one clock cycle. But then what is the capacity that we should think? Okay, the capacity of the on-chip memory will be very less, where the capacity of the external memory will be more. So what is very important for us is to understand that what kind of resources it is taking and what kind of resources we should fit in for. That information is also required. And one more important thing, what is required is the kind of coding when we follow, that it may try to take, okay, different set of operations based on the fixed point as well as the floating point. And what is very important is the kind of operators what we use, right? For example, when we try to write an RTL code, we would avoid writing the block multipliers like the star operators and then division operators and the percentage symbol, etc. Because we knew that those kind of block multipliers is going to provide you a different set of area. But what we will try to do while writing the HDL code is like, we will think that, okay, what kind of operators are required, or they are going to provide you synthesizable logic. That means which are supported for synthesis, right? Which are not going to provide you good optimization logic. All those things we will think, okay? Similarly, in high-level synthesis also, we can check from the loop analysis report to see how the loop is analyzed and optimized, and we can follow specific coding guideline techniques to ensure that all are taken into account. Here you can see how the loop analysis shows how the loops are implemented. You can see that it shows that the initiation interval is 1. That means you can see that that could be possible with 1 clock period. But then here it shows that it is due to memory dependency. That's what I explained to you. And you need to see that what kind of techniques that could be adopted in order to perform. So you can see the bottleneck here. The bottleneck specifies that what is the problem with the code and how that could be rectified. Here it shows that in the 18th line, right, you can see that it shows the initiation interval, which is 2 clock periods. From the HTML report, when we expand it, we can see that why that kind of logics are getting generated, we can get into it. So just to get a quick glimpse, if you expand this report, you can see that it shows that there are different set of logics, and it shows that it takes 2.7 clock cycles for performing the integer compare operation, and it takes 2.2 cycles for the 32-bit integer multiply operation, and it takes 1.7 clock cycle for 32-bit integer adder operation like that. This gives you a clear picture of, for each and every operation, how many number of clock cycles are taken, and we can understand what is this bottleneck. You can see that it takes 5 clock cycles. And why it takes 5? Because you can see that is the data dependency. All this information should be shown, which you can get into the details later. So in the area analysis, there are two things which I mentioned. One is we analyze the data control overhead, and we view the memory implementation. So it shows the resource usage, ALX, flip-flops, RAMs, and DSPs, and identifies the inefficient uses which are available. Now we come to the memory viewer, which is the local memory implementation access, where we can visualize the load and the store unit. So what is the problem for load and what is the problem for store? So that information we can get into it. Now, I have also shown you about the viewing the component waveforms with respect to the Model Sim Intel FPGA Starter Edition, where we can see the simulation waveform that is available where when you say after performing the co-simulation process, you can see the waveform that is available inside the project verification. You can see vsim.wlf. So that should be available inside the verification folder. So after the process gets over, we can get that, okay, inside that particular folder, you could see inside the verification folder, you can see that vsim.wlf. You can see the waveform file that is present inside the test. And we can view waveforms in the model sim simulator for the specific logic. We can locate the component on the left hand side, right, and you can also see the output here. This is my mult is the instance, which is a function, which is a component in our RTL code, and we can see the waveforms with the model sim simulator. So this is what is shown to you, where you can see what is the component, what is the frequency of the clock, and what is the estimated resource usage. That information is provided, and we could see in the summary page about all the details in the report. So you can see the quality of results data, so that will provide you the final resource utilization, and we can also see the Fmax. So whether the Fmax will help you to perform further optimization, or if you want to take any specific decision, then we can utilize that as an option. Right. So once we get all these details, what is our next scenario? When we say in the project components, we have all the files to be integrated. So what we can do is we can instantiate that in the HDL, or we can add that IP to the platform designer system. So we will understand more about platform designer in the lab session. Then we can understand how we can add that as an IP. What are the possibilities I showed you? Number one is like you can directly see the instantiation, which is present as an instant.v, which is the component.qsys, right, which is the Quartus system integration file. And you can see QIP, which is for the Pro edition. And we are going to use the same light edition, which is exactly equal to the standard edition. And we will be having the QSys file, and we can use that as the template. And you can see on the right hand side, we can write what is the instantiation logic that could be connected. It's .clock, .reset, .start, busy, done all the components to which it is connected. That information we can provide and perform the instantiation appropriately. So after all these things, then we can take it to the platform designer system. So you can see all the components would be integrated, and then we can automate the integration tasks with respect to the platform design. So this is the way how that could be located. So I can just show you a simple glimpse of the platform designer before we summarize this. Right, so let us go through that. So we open the normal Quartus Prime design software. Let us create a new project. So just say platform designer, and then we'll say, for example, something like that. You create, let it be anything. So top. So we can target it for any device. Let us target it for Max 10. We have discussed about the Quartus Prime design software, and then we perform timing analysis, right? And then now if you click the tools tab, what was discussed earlier, run simulation tool, timing analyzer, planner. In the netlist viewers, we have seen RTL viewer, technology map viewer, post fitting, and state machine viewer. We have also seen programmer. Now what we wanted to do is the platform design. You can see when you click tools platform designer, which will take you to the platform designer system. What is the fundamental difference is the IP catalog is provided on the left hand side, right here, and then you can see that it is available. The IP catalog is available on the right hand side in the platform design. So you can bring any intellectual property, and that could be connected in the platform design. I will just show you one simple example. I wanted to take a memory. I type here on-chip memory. You can see on-chip memory, RAM or ROM, which is available as an intellectual property. You can take that, you can use it at a single clock operation, because by default it is showing a single clock operation. But then you want to use a dual port memory, then you can click this dual port access, which can show you different clocks and different slave operations. If you don't want, then we can just uncheck that. You will get a single clock operation. And now you can see that, okay, you wanted to connect it, so you can say this is connected to the system, right? We can see in detail how they are connected. But now you can see that when clock must be connected to a clock output, you can see multiple errors. How do we connect it? When you say there are two ways to connect it inside the platform designer. One, you can just click open dot. That itself will directly make connections. So that is the greatest advantage of the platform designer. Another one, if you wanted to connect it, right, instead of clicking the open dot, you can also say right click and you can connect this to the reset. So you can also perform connections like this. Now you can see there are no errors. So like this, it is only not the memory. So what we can do is we can bring the processor, we can bring the memory, we can bring all the peripherals like UART, right? And then we can connect them, JTAG, UART, everything, and parallel input output. And we can connect this to the platform designer and integrate the system, right? So that is also possible. That's what, along with the Quartus Prime design software, it is also possible for us to create the system, right? We will get into the details of this platform designer lab in the afternoon session, which includes the processor, memory, all the peripherals. That will give you a clear idea to generate the HDL in the platform designer system and integrate that in the Quartus Prime design software. You can see that there is a generate HDL, which helps you to generate the HDL of this, all the components. Right, so this will also provide you a clear picture. Here you can see that there is a QSys file, which is a Quartus system integration file of the platform design. Right, so let me stop here, and then I request Ipsita to continue with the high-level synthesis flow.
Hi.
Over to Biplov. Biplov, can you please introduce Madam?
Thank you, Patna sir, for such a nice session. Next session is on HLS implementation of 32-bit square root component. It will be taken by Ms. Ipsita Das. Before that, I would like to share her brief profile. Ipsita is the Intel PhD engineer working on Intel Open FPGA stack, Intel OFS hardware acceleration platform development. She has over 18 years of experience in FPGA-based system design and validation in ATM switch, WiMAX, 4G, LTE, storage products, etc. She holds bachelor's degree in electronics and communication engineering from NIST, Berhampur, Odisha, and a PG diploma in VLSI from Sandipani, Bangalore. Madam Ipsita, madam, welcome to the session. I made you the presenter now.
Thank you.
Over to you, ma'am.
Thank you. So I'll just go ahead and share. Hope I am audible.
Yes, madam, you're audible.
You're audible.
Hi everyone. Welcome to the lab session of Intel high-level synthesis with Intel FPGA. I will basically walk you through one of the Intel HLS lab demonstration. And before I begin, I would like to thank ICT Academy, IIT Guwahati for giving Intel this opportunity to interact with all of you. I hope you all have got a good understanding about the Hls Flow in the first hour by Padmanabhan. And it has some of the basic concepts around this. So now we will have a practical approach to what Padmanabhan had demonstrated in the first hour on the HLS flow. And we will be using a very simple C++ example program here. So what are we taking here for a demonstration is we'll be taking a design component called floor square root. This is written in C++. So basically this function will find the floor of the square root of a given input number. Okay, and then we will go ahead and synthesize the floor square root component to an RTL design using HLS compiler. So we have an introduction about what HLS compiler can do. And here we will see that how a C++ program is getting converted into an RTL design and usable then on as in the RTL flow. And in this example, we are planning to enable the same component, the floor square root component, as an Avalon slave device. So why are we using that? Because if we enable, suppose we want to use it in NEOS kind of platform designer, right? So NEOS is basically a soft core processor, and that needs Avalon bus interface to interact with the slave devices. So if you are converting a floor square root function, if you want to use it, is this IP as a slave device for a NEOS kind of platform, then we should have it. It should have a bus function as an Avalon interface. If we enable that with the Avalon slave interface, then we can easily connect it to a NEOS-based system using platforms in Designer. So after doing that, we will be compiling the component using a Quartus prime. And then we will analyze all the reports, how it looks in resource utilization, timing analysis, etc. So this design, you can take it up further and you can end use it in some platform, some hardware platform, right? So we will leave up to designing it as an IP component, and then you can later you can try it using in any of your existing platforms. So this session, actually, the plan is like we will run the HLS compiler steps. We will emulate and co-simulate the HLS component using HLS compiler. So we have already gone through the steps of what is emulation and what is co-simulation in the previous slides. So here we will see in practically how to execute that command and what in each step it is basically gives out as an output, each of those command lines. Okay. So let us start. And before we start in the lab session, these are a couple of assumptions. So this particular lab manual will be shared with you, but you have to make sure that before you start the lab, you should have a Quartus Prime Lite edition 18.1 installed. So like I have installed in my system, and you see, like in my C drive, this is my Intel FPGA Lite 18.1, which is installed. And here you should see the HLS as one folder and one installable here. Okay, so why I am showing you this, because this is important for this session to understand. So if you get into the HLS, you will find there is a batch file called init_HLS. So this is an initialization batch file, which will initialize Intel HLS, various libraries, include files, various paths. Okay. After running this batch file, we can execute the HLS compiler, basically all these I++ command that can be executed once we run this batch file. So any project that we start, we have to make sure that first we do run this batch file. And you have to point to wherever you have installed your Intel FPGA Lite 18.1 version, or in future any other versions that you load, you have to make sure that you have pointed into this path. Okay, so this is specific to your system. So in this, you can see there are certain example folder. There is an example folder, and inside there are a couple of examples. So this is also something you can go through and can run this on your own to find out details. But however, I will take a specific example, not from this list, but another example for you to showcase. Okay. So apart from the Quartus Prime Lite Edition installation, we should have Model Sim. This comes as an embedded along with the Quartus installation. So we can reuse that. Should have Windows command prompt, and we should have the Visual Studio 2010 professional trial version. So that we will be using for today's lab. And there should be an understanding of Quartus Prime Lite development tools. Some basic understanding is required before you start using this. And this HLS quick start source files zip file. So this will be shared by us to you. So this file will have basically this set of files in it. So what are they? Like, we have the lab manual here, which I'm currently showing it to you. And there is one program which we are planning to execute in the demonstration, that is the floor square root .cpp file. And then we have all the commands that we will be executing for this. That is also, it's part of the same package that you will find. So we are using the emulation command, then the co-simulation step, then showing the co-simulation executable we are putting here, and how we will see the waveform file. So we are using model sim, so the similar command vsim is been used. So I'll go through this step by step so we can have more details. Then we have a setup.txt. So this file basically, so if you see here, we are first calling the init_hls.batch file. Okay, and then there are a couple of installation path, include and library paths being set, and certain aliases which we will be using later for Quartus. And one thing you have to make sure that the path that you specify should match to your path, basically your installable path. So let us go back. Okay, so this is what we will be doing the lab session. So the component that we are planning is a square root component, and we have HLS, the Avalon memory mapped slave interface attached to it. So we are doing it in order to have it placed in a kind of system where NEOS is the processor. This kind of system we can attach this. So that is why we have a Avalon. Otherwise, if you do not need, you need not have to place Avalon slave component, but you can have a something separate interface, or you can have it as a standalone component and use it in your RTL flow. Okay, any of this thing based on your design requirement, basically you can try. So this is a little bit about the flow, which I will just reiterate of what Padmanabhan has already given. So for HLS flow, the design component that we will be using, both the design as well as the test bench, is written in a high-level language, which is a C or C++. Okay, and then what we will do, we will after we have the design ready, we will start with the emulation step. Okay, so emulation is we are using the I++ compiler to perform the HLS for the emulation, and machine architecture we are specifying as X86 64, because we are doing the emulation targeting to our host system currently. Okay, then we can also use like a GCC or a G++ compiler, and the executable we can run in the host machine. So in this step, we can do a software verification, and we can use various debug techniques like printfs or GDB, etc., and can fully verify this design functionality, but in a software environment. Okay, so why are we doing so much in this step? Because we need not have to have all the functionality getting tested in once we port it into hardware. So this is again to save the design effort and time in a hardware environment. As we all know, it is a time consuming process in a hardware simulation environment to test all the functions. Okay, and not just time wise, but also effort wise. Anything that we convert into hardware and prove the verification or any other step requires more time. It's a time consuming process. So we will do the maximum possible in the emulation step. Okay, and here we will gather all the confident approach to our design functionality. So then we can move on to the next steps. Okay, so next step is a co-simulation process step. So here again we are compiling the same design in I++, but if you see the machine architecture, we are setting it into a device, FPGA device. Okay, so here we have set it for a max 10 device. And whenever we do a test bench in the co-simulation step, it is co-simulating in a software test bench is there, but the hardware Hdl IP has come into picture. So why the name is co-simulation here? We are basically simulating coexisting both the software test bench and the hardware IP using a hardware simulator. So the simulator is a hardware simulator. Here we are using Model Sim as a example for today's lab. But the software test bench, we are still using the software test bench. And now the IP also, the HLS component has converted into an RTL IP. So these two things making it as a name as a co-simulation. So now you can ask like why that we have already verified the thing and the HLS component in emulation, then why we need to reiterate the same thing here. So yeah, that's correct. We have verified the component in emulation step, but in co-simulation, we are verifying in a hardware simulation environment. Okay, so hardware simulation, when we say, it is basically an event-driven simulation, and it is a near representation of the hardware behavior of any component. And main thing here is like we test the latency and performance of the component. And if there is any other hardware related issues like generation or any step we get issues that this part of thing cannot be converging into hardware. So we can rectify that in this stage basically. So this will again give a simulation environment, so we can verify the component again, okay, which is now Hdl IP, and we can get a simulation waveform simulation here to verify the design component. Okay, so I will show you how that waveform simulation looks like, the feel of it we will discuss that while we are going through the steps. So we are still using the software test bench, but we have a hardware IP now. So we have already seen, I mean, in the previous slides by Padmanabhan, that in order to interact between a software test bench, which is written in C or C++, with that of an hardware IP, which is now converted into like system Verilog kind of language construct. So the HLS compiler will basically generate DPI interface. Okay, so because one is like a foreign language here, which is a software language, and other is like hardware language. So in order to interact between the software and the hardware interface in a verification environment, we use the DPI. DPI is the direct programming interface between these two language interactions. Okay. So another thing about co-simulation I want to bring here, that it also does the HDL compilation, and it will generate various reports for that particular IP. Okay, so from these reports, we will get an approximation about resource utilization of the IP and what maximum frequency in which this IP can run. So when we target here different devices, we also get into different, the reports can also vary. Okay, so I guess you all already have gone through the sessions about FPGA flow and various FPGA devices, and so you will have get that idea about what it means, right? So this is what, and you can, if you want, you can bring this IP into any platform, whether it's a NEOS2 based platform or any other platform. So here we have targeted for a Max-10 device. You can target to any other devices. But if you're targeting to a Max-10 and a NEOS, Max-10 has a NEOS, so you can use the similar flow basically to put it in a NEOS-based system. Okay. And next step is the compilation, and we will run the Quartus prime compilation on the new component, and it can be ready for any hardware, downloadable for any hardware board finally. So there are software steps and all which you can probably do in your other sessions on how to have a NEOS based system, then how to have the NEOS software build to have any software that you want to run in your NEOS system. Okay, so that anyway we are not covering in this particular lab session. So hope you are clear on this. I'm basically reiterating the steps before I get into the lab. If you have any doubt on these steps, you can just put it in the chat. We'll answer you. So so now for the lab, you have gotten the, you will get this zip file that I have already put here, and so in the first step, we will invoke a Visual Studio command prompt to start on the lab flow. So I have it already installed in my system. Okay, so let's go to the lab files. Here you see we have a setup.txt file, right? So first we need to do the setup before we start running any other command. So I had already shown you this where we have to first call the batch file, which is the initialization, HLS initialization batch file, and setting up certain library paths, etc. So when we have to run this as a batch, let's convert this into a batch file so that we can directly run. Okay, so let's go to this location and let's run the setup.batch file. So if you see, it will give you something like this, which will initialize all the paths and alias, and it is also showing that it is using this path, find quarters. Yeah, so all the steps regarding setting up and initializing is actually completed. Okay, it is running this batch file and all the steps. So we have completed this first step. So we have done this. So you are also seeing this. This will tell you that, okay, your setup is good. If you get any error here, so you have to basically go and check what is wrong. You have to rectify and should get something similar to this, that it has been initialized everything properly. Okay, so now we will go to the function. So we have only one file, if you see here. So this is the floor square root.cpp file. Let's start here. So we have include files like HLS header file and stdio header files. HLS header file has it has HLS attributes on explicit interfaces, and stdio anyway we will use it for printf supports for components during emulation. Now let's come to the component. So this is basically our function to find the square root. So this is the C++ program square root function that we are planning to convert into an HDL IP. So currently it is a C++ program that you are seeing. Okay. So anything that which is using the name label as component here. So if the name label is component, the Intel HLS compiler will create a corresponding RTL module for it. So when we execute this code in a Intel HLS compiler or use a command I++, say, for example, so it will search for these items or these names. Basically, if it is component, then it will infer it as a RTL module, not anything else. Okay, so suppose you want to keep multiple such IPs, you can go ahead and keep, but you have to label them as component. Okay, and then only your RTL modules will have ports and interfaces that will allow the system to interact with the HLS component. Okay, and by default, if you use the name component, the HLS component in a RTL, it will by default have two interfaces. One is called call interface and other is called a return interface. Okay, so let me show you that just to give you an idea of how it is. So this is a HLS reference guide. You can download it from web. So whenever you use the component keyword, as I showed you there, it will have something like this by default. So there is a component, whatever name, depends on what name you have given, basically, and it will have a call interface and a return interface. So call interface is basically to when processor or somebody which a controller wants to interact with this component, or the devices which is sitting on the left want to interact with this component, it will use this interface signals, say start, and the component, if it is busy, it will give out a busy signal. Then the controller would not begin a start, basically. So it has to poll the busy and then it will go for start. Start in the sense it wants the component to start its operation. Now the component, if it's done some calculation, it can say via these signals like done. Or if there is back pressure or they want to stall the component, the signal can be used. So these interfaces comes by default whenever we use this word component. Now, apart from component, if you see, we are using a HLS Avalon slave component. Okay, so this is what we have declared our component as. Then the design will not have only these things, and these things will not be these signals will not be like a conduit interface, exist as a conduit interface, because now we want the Avalon bus interface to be connected to the component. So it will show you something like this. It will develop a CSR kind of interface. So CSR means it will have a control and status register interactive interface. So controller, if it wants to interact with any slave, it will go through certain bus structure, right? So here we are using a Avalon bus structure. So Avalon will have this set of signals which will interact with the component, but to the component also it will interact through a CSR interface, okay, a register interface basically. So if you see here in the Avalon signals wise, it has address, read and write enable signals, write data, read data, and a data valid. And also there is interrupt, separate interrupt. So whatever we wanted to do to the component, like we wanted to say, for example, this particular component has A and B inputs, and there is a return data. So A and B inputs to this module has to be written via this register interface. So they will have their own place as registers. And similarly, start, if you want to start the component operation, you have to write through a register. Here you, in the sense, any controller which is sitting over and interacting with the slave device, it has to come from there and it has to write into the start bit saying that start the operation. So this component, your component will basically start, and whatever functionality, suppose it wants to do a plus B or A multiplied B or whatever function it wants to do, it will do, and it will return the data into register back to the register again. And it will say that done. So done is again a register bit which the either it has to be polled by the controller, or there could be any interrupt to be given to the controller, so that the controller will come and read the status, and then it will come and read the data. Okay, so in this example, for the square root, floor square root, we are connected it to a HLS Avalon kind of interface. And we are using a HLS Avalon slave register parameter. So this is basically a parameter interface attribute. Okay, and this is the component CSR, which can be written to Avalon memory mapped slave interface. Okay, so this is basically the program. We can go through that in steps. So this is the function itself, which is calculating the square root, and we are using certain pragmas compiler directive, which is specific for HLS, and max concurrency we have set it as 1, which means that the number of iterations of a loop, of a single loop basically, executed number of loop that executed simultaneously will be 1, which means the loop will execute without any pipelining. Okay, so this is about the design, and the test bench also lies here. So in the test bench, we have 4 different type of values, x values, and if you see, we are calling the x here x1, x2, x3, x4, and we are calculating the square root function, and given it is in the output. The outputs we are using as printf statements, and also we are checking whether those outputs are giving out the correct value or not for printing the error message. So here you will see that we have one number which is not a perfect square, 257, and that we are expecting it should be floor squared, and we should get 16 as output. If we do not get that, then that will be printed as not correct. So we will use the same test bench, which is here for both our emulation as well as co-simulation. And the design also we will be using for emulation first, and then the converted RTL we will be using for the co-simulation. Okay, so let us get back to the lab manual again. So first step we will try is the emulation step, and the command for that is this I++. Machine architecture is x86 64. The input file we are using is the floor square root.cpp, and our output is a execution file. We call it as a name emulation. So if we do not give anything, it will be A, which was shown by Padmanabhan in the initial slides. So here we have given it a name, emulation. So let's copy this step. We can copy here, or we have the list of commands. You can copy from here as well. So if you see, it has given out the execution already, and it is done really fast if you observe. And if you run this executable, we can see the floor square root of those 4 values that is there in the test bench has been basically tested on the design. And we see the outputs displayed here, and there are no errors also being reported. So this makes sure that okay, our design is tested, or whatever we wanted to try. So if you want to elaborate your test bench, you can definitely go ahead and do. And this is a smaller design that we are trying. When you have a bigger or complex system, your test bench can also, you can have many more cases included in that. Okay, so this is about the emulation step. So we will next go to the co-simulation step. Okay, so for the co-simulation, this is what the command we will be using to run it. So the command is I++ again, and we are using here -ghdl. This is basically a command line argument. We can have multiple command line argument, and you can choose whatever you want to use for your simulation, or for your compilation basically. So we have used -gsdl because this command line argument, when we use, it enables the HDL signal logging in the simulation. Okay, so we can view the signals in the simulation, and if you do not use it, we will not have signals to view in a simulation window. So we can use this, and it will enable the debug visibility. It will have debug visibility as well. So we are setting up machine architecture now to max 10 device. So now it is specific to which device we are planning to target our design. And again, remember, if you have a architecture set to different devices, your result can vary. The maximum frequency in which it operates, or maybe the size of the device of that IP can also vary. If not majorly, but to some extent it will vary. But frequencies, maximum frequency can vary largely. Okay, now let us go ahead. So this is the input floor square root.cpp file, and co-simulation is our output executable. Okay, so let us go ahead and go for the co-simulation step here. So it is still going on, and if you see, when we executed the emulation step, it happened really quick. We just enter this line and we just say enter, and it was done. So why that it is taking longer time? You see, the compiler time takes nearly 3 minutes of the design. Okay, so now why it is so happening? So emulation is actually, earlier emulation is purely software design and verification, whereas co-simulation, what you are trying, is software test bench now running in a hardware HDL IP component. Okay, so there is interaction between software test bench and the hardware component. And as I told you, like we have the system verilog DPI also in between. Okay, so here it is not directly writing into the X component like you are seeing in this test bench, right? We are seeing like in a software test bench, we are just putting the value X and it calculates the square root and gives us. But in this case, hardware case, now it is an Avalon interface, and we have a whole CSR interface to take care. So the writing and reading now happens through a CSR interface. Okay, so there are so many things, and that is the reason why the time it takes to do that. Okay, so comparatively higher time.
Meanwhile, can you answer a question in the chat?
Sure, go ahead.
Yeah, does it support the data in textual word file? For example, when we process sine, cosine values to verify any algorithm at the RTL.
So that sine or cosine value, you are writing it in a C or C++ file, right?
Right. It supports the data in the textual word file. Yeah.
Yeah, that is fine. So if it is a if it is a .cpp file, that doesn't matter, like what you are using, whether you are using a notepad or something else.
Right. Yeah. Thank you.
Sure. Yeah. So now it has completed, and we can see that we have the co-simulation executable already in place. Okay. And what else it has generated? Okay, we will see now. Now we will go through in details. So here, if you see, we have a PRJ file, and the same thing Padmanabhan had already discussed and showed it to you. So this is got created when we do the co-simulation step. Okay, so in this PRJ file, we have all these folders, which we went through also, but we can have a little detail of what they are. So first thing is the components. Okay, so components, if you go, you see we have only one component here. So why we have a single component here? Because that is what we have written the function for one component. If you have multiple components, you can have multiple such components being declared here. Okay, so now we have single component. Now let's get in there. Okay, so we are seeing there are so many outputs. So one of them is a .qsys file. So .qsys file is a platform designer system file, which will be used by platform designer software. So if you are bringing your design, the square root function, to a platform designer system, or suppose you are making a NEOS based embedded system, then you can directly take the .qsys file there and attach it. You don't have to be worried about instantiating anything, and that is what the how platform designer tool is so handy in using and making systems in no time. So this kind of qsys file will be a basis for there to be included. And if you remember, we have already made the this is as a Avalon slave component, so it is moreover easier now. This qsys already has the Avalon slave interface there. So if you just bring in the qsys and attach it into any platform designer, which is a Avalon based system, it will automatically does the interconnect for you. Okay, so platform designer tool is capable of interconnecting this. We just have to bring in the device, bring in the IP, and just drop in there and connect. Rest of the interconnection, it will do it. So for the qsys, if we are going through, we also should know what is this hard vertical file. Okay, this square root internal hardware.tcl file, this is a hardware component definition file, which describes and package the IP component. Okay, so square root related functions you can find here. Maybe let's just go through and it will give you some idea. So this is a qsys, and you see what are the synthesis file sets. So it is using so many files internally to come to and bring you that IP in HDL. So this is your HDL realization basically. So all the files that is required to to convert the software code, which is a square root function, into a hardware IP. These are the set of files. Okay. So you see all these files, they could be very small files, okay, but they're all come together and become that. Then we have, those are the design sets we saw. There are some simulation file sets are also there. Okay, so this is what is a hardware-tical file for this square root function. Now, what else we can check here? Instance file we already know. So suppose you are not using this .qsys, you just want to use the square root instance file for your some other design. You want to manually do that. So take in this instance file and put in your signals on these sections where you want to connect it into. Okay, and on the left hand side, whatever you are seeing, it is a part of the square root function itself. And the right hand side is your connectivity that you want to connect to your system, wherever you want to connect this function to. So instance files comes as handy there. And we have another interesting file here, which is a csr.h file, square root csr.h file. So what is this file about? So we remember that we have our C++ file square root, okay, is basically is a component having HLS Avalon slave. So if it is HLS Avalon slave, we have a CSR interface, or that is a register interface to interact with the IP. So this is of importance. So if you are seeing this section is having all the CSR details, which says what is the register address, and that register, how wide is the register? It is a 64-bit here, let's say, right? So in the 64-bit, first 63-bit is reserved, not used. Only the 0th bit is used for busy, and it is a type of read access. So this information basically goes, and there is a description, of course. So this information can be handy for the software. So the software can just take this much, and from the description and all these details, you'll understand, okay, if I have to interact with this IP, this is the way I have to operate. Okay, so you see there is a busy bit, there is a start bit, all these bits are mapped to registers, and then there is interrupt enable, because we have a single interrupt out here, right? So interrupt enable, interrupt status, and done. Both these statuses are present in this address. Then this is the X input that we want to calculate the square root upon, and this is the return data. Okay, and you have the description which tells what is for what. So all these information just got generated when we just do the co-simulation step. So if you see how much amount of work the tool has done for us and making it usable for a designer to bring it into for a project, it becomes such a quick turnaround. So yeah, so these are the details of the registers, which a software controller, for the controller or the software, this will be useful. Okay. So we know where to find those information. So that is why I just wanted to show you. So this is where you can find those information. And let us see this, the IP folder. So you see for the square root IP, all these files have been used. Okay, so there could be small design files. Each of them maybe you can go through just to see how it is. But this is the list of files which has been also put by the simulator, the co-simulation step. So now let's come back and go to the next folder, Quartus. So Quartus project file. Okay, so this is for the individual HDL IP. Okay, and yeah, we know that this is the project file, this is settings, and this is a compile file. So let us go through the compile file once. So same IP, basically the same IP, they want to give an example where you can see the details of the IP in a Quartus environment. You can quickly just open this QPF and run the design. You can do that. Okay, so if you do that, you will get an idea of what is the uh, what is the actual device, sorry, resources can utilization. You can run the Quartus and check that. Okay, and you have all these infra already ready for you. So settings file where you can either put your pin details, wherever you want to end use your design, or anything, or any other details for the Quartus settings you can put here. Then there is a .sdc file where you can define all your constraints, synthesis constraints. And there is a wrapper file also. Okay. So this is the Quartus compile. You can go through the compile design, run this step, and can generate all the reports for that particular IP. And here main things that we can cover is like just to show you that in this compile, if you compile the IP, we can check the reports like resource utilization and what is the maximum frequency in which this IP can operate. Okay, so for this we can go to various reports. Let it run and I'll show you what are the report sections you can go. But yeah, we will not go to details, but however, just you can check the exact section for that. So let it run. We will come back to that. So that is about Quartus. And then there is another section called reports. So already Padmanabhan had gone through details of what this report is. So I will not be going into details, but again, just want to show you that this report section is for the IP, and in the co-simulation step, we generated it, right? So they have, all these reports have been put together beautifully in this just one single HTML page. Okay, so which you can go through, and you can go through summary, loop analysis, all the steps one by one, and you can see that where you can better your design or modify your design, or you see there is some issue looking at the report, that you can go back and check your design and correct it. And we are still not in the hardware flow yet. So this is the best step again to check any other functionality that you intend to basically design and it has not achieved that. So this is a area where you can look at and rectify that basically. Okay, so you see that we have these logic elements and flip-flops and all the stuff being used. So are you sure that this much design resource utilization is fine to have this kind of function? Okay, if it is fine, then okay, fine. That is your resource wise, you are okay. You can go ahead. If you are not, then what you need to do? So in this case, you see whether your function you can write in a different way that it can have a lesser resource utilization, or whether this device is not fit for this particular design. You cannot fit this because it is not the only component or IP that will be present in your design, right? You have could have hundreds of other IPs, and they are already consuming so much of space, and you cannot accommodate probably this one. So you can think of whether it can be done in a higher device where I can put this. So something like that, this kind of decision making you can practically do by looking at these reports. Loop analysis, yeah, already Padmanabhan had gone through, but just to that, if you check these kind of loop, it says what kind of pipeline loop or initiation interval is how much, and it will take you to that loop. So if you have many loops, in this particular design, we have only one while loop, but if you have multiple loops, then you can basically click there and you can analyze and see whether that is what your intended thing is. Okay, so if you have any questions, do let me know. Padmanabhan, is there any other questions?
No questions, Ikshita.
Okay. Okay, so the last thing that, okay, let's go back. This might have
Yeah,
completed.
there is a question about what about the timing values in the report?
On this report? In this report?
Yes, yeah.
Okay, so here we will only get a maximum frequency kind of information. So more details if you want to check on timing wise. So, okay, maximum frequency, if you have targeted to a max 10 device and it is suppose showing you some 100 megahertz kind of maximum frequency. Whereas your device has to operate, your design has to operate in, let's say, 400 megahertz. So then you cannot take this design. So, but again, can you achieve that in a max 10 device, or you are looking for higher devices? So that is when I initially told you, like, if you want to target in a higher device, probably you can see that the frequency of maximum frequency of operation had increased. So that kind of details you will get here. Now, if you want to get more timing details, then you put it in the quarters, give out the actual constraint that you want to use. Okay, so I had shown you this section. There is a Sdc file. This file you should go and edit and add your specific constraints that you're looking for and rerun the quarters compile. And you will see if it is meeting the timing or not. Okay, so currently probably this gives out probably a blank kind of SDC, not much details. So there is no pin constraint. Of course, we don't know what to be put there. So that is what this, see, this is doesn't have much information of the constraints, given constraint, because this is dependent on your design where you want to end use. So that is why it will always vary from project to project which constraint you want to give. So fill in those constraints and rerun your design. And you have any timing issues, you have to analyze here and rectify, try to rectify that and see that how in your software program you can take care of that. Okay, so I think the last thing here is the verification. So verification, I want to show you the simulation. We have a tb.v file. So let's open this. This will be interesting for you. Okay, so this is a TB test bench file, top level test bench file, where it instantiates number of things. Okay, so the duty should be there. So duty will be somewhere here. This is our duty, square root function. But if you so apart from duty, we have other components here. So why would that be required? Because we know that our software verification or test bench is there, which we have to interact through a DPI to our hardware section. So hardware IP. So because it's a synchronous system. So we need to have a clock and reset generation. Okay, then the DPI controllers, these are all been inferred by the co-simulation step. So it brings out the DPI components here. This is a place, this is a framework basically. It is not that the final thing. If you want, you can play with your test bench, even taking this framework and develop on top of it. Can be done. Okay, so you need to understand how the interconnects is been mapped, where it is going, and where you can place your own test bench also if you want to do some experiment on the test bench side. And here you see that there are various simulator options are there. Okay, so here we are using mentor, say for example. So we can see what are the setup script, TCL script, what is the compile. So these details we can also check. So it will set up all the simulation libraries for that, and various paths for the simulation. So this is also a place where you can edit to some extent. And you need to understand, basically, if we are using any simulation, we should understand these files, and we should able to modify them as well. Now there is a wave file.
Yeah, we're hearing some background noise. Can you please mute if someone is not
Yeah,
having
I'm
any
also
questions?
hearing some background noise.
Yeah, thanks. Yeah, fine, thanks.
Where is the waveform file? I think it is there inside the quarters. Let me go through this step. So we have covered the co-simulation. Okay, it is inside the verification itself. Okay, so we will execute this, and this is the wave file that we can view now. Let me open this so that you will get an idea of what I meant here. So if you see, the vsim is basically for model sim. This is the command used to open the simulator. And here we have given the WLF file. It has already been generated. I do not see the waveform. No, this is not. This has not generated the waveform file. Let me see if I missed any step. Oh, I had not run this step, the execution. So co-simulation.exe file, this executable, if we run, it will basically give out the vsim wave file. Okay, now we can. I had missed that step, so that is why you're not able to view it. So now it has created. So the steps, basically we can follow the commands. So we had done till here. Now we did this step, and then we open the vsim using this step. So now it is trying to open the model sim. So this is a model sim simulator, and we are trying to open the waveform file, which is for the square root. There is already a wave.do file. Let me show you. In the initial zip file, we had this existing wave.do file. So what is this do file? It will basically have a list of certain signals that we wanted to show you today. However, you can modify this file, or you can create your own. It can be done. So anybody who is so far familiar with model sim can do it. Otherwise, also you can follow some tutorial on model sim to execute that. Okay. So I had this existing wave.do file, so which I have opened here. However, you can have your own. So say for example, this is the top TB file, and this is the square root instance. So currently, whatever signals we are seeing here, looks like from here. So, but let me delete them. I don't want these signals, but I want to put this set of signals, which is from the square root instance. So I can just drag and drop, and we can go from there. I will make them, say, hexadecimal type. So this is the clock and reset. These two things have been generated by the test bench. And first we will see that we have a write request. Okay, so let's go here. So let me enlarge it a bit. Okay, so so the first write operation we see is this. All these things is coming again from the test bench, the same test bench that we are seeing here, right? So same software test bench. And finally, all these information, right, where we are making a square root, it's all coming from all the way from the software and through the DPI to the test bench that the co-simulation have created for us. So in that test bench, again, it is a CSR kind of interface. So you are seeing here the read, write, enable, address, write data, byte enable, and read data. This is the interface that it will use to now interact with the square root IP. So what is the initial thing it is trying? The address is 2 and the data is 1. So basically the addressing would have been bit changed. If you see the CSR, here it will be like an word boundary because we are using 64-bit. So the byte level address, if the processor is doing, so we are like skipping 0 and 8 and 1 0. That is the kind of skip happens. But however, internal to this module at the square root level, we are not following those byte level. We are directly going into the 64-bit level. So okay, so now the address 2 is basically the interrupt enable. Okay, and it is making it 1, which is making the interrupt enable as 1. Then second is 3. So it is like 1 1 followed by 000. So 1 8 1 8. So it is making the status as writing 1 to clear it. So it is writing 1 there, and then it is coming to 5. So 5 is 101 followed by 000. So it will become 28. So 28 is basically where we are writing the input argument, which is X. So the first data we are writing 4, if you see here. So an address 5, let me enlarge it a little bit. And this address, we're writing the data 4. So that is the first data that we are trying to find the square root. So you can refer even the square root. So this is the first data we are trying, right? X1. That's what we are trying here. So 4 is the input that we are giving. So finally, it is coming in a CSR fashion, and it is writing 4 in that. Okay. And it is giving a byte enable of 0F. So which means the first 4 bytes are enabled. Okay. So first 32-bit, it is a 64-bit. So first 4, that is the first 32-bit is for the data. So we are basically using a 32-bit data interface. Okay. Now, after we write the data, we are writing into register 1, which is 1 followed by 3 zeros, that is 8, equivalent to CSR 8, which is we are giving it we are giving start. So start means the signal will start the component. So we are writing 1 here, and so it starts. Now let's minimize a bit and let's see. So now once we give start, this internally to the component, it will start doing the square root function. Basically, the RTL equivalent of this is now coming into picture. Okay, so we know there is a loop and it will see the value and it will try to come to the square root with a certain number of loops. And it comes around at this time when it says done. So done is basically an interrupt going from this component square root. Okay, once this interrupt goes, and let's say the processor sitting here, currently for us the test bench is our controller. So let's say the processor sitting there, it will know that it has done and it will come and read the status or whatever. So here the test bench is handling it. So once he sees done, it comes and it starts with address 4. So 4 is again 100 followed by 000. So it will be 20. 20. So 20, it is having the return data. Okay. So the data, the value that we see here is this one. So this is the read request and we get the data after 1 clock because it is synchronous in nature, right? So we are getting the data as 2. So square root of 4 is the value 2. Okay, and then we go ahead and then we does on 3, which is 3 1 1 followed by so 1 8 1 8. So we come and what are we writing there? 0 1. So 0 1 is basically we are clearing the interrupt. So this interrupt that was been raised, we are again clearing because we have read whatever we wanted to read. Okay, so we cleared this. Now it is ready for the next set of instructions. So interrupt is after we write this internally, it gets cleared, and then we are ready to take up the next set of instruction, which will be here, which will be 36 to 57 and so on. Okay, so there are some 4 values which will follow. And what else I wanted to show you? Any questions so far on this?
Yes, there is a question, Yogita. In the model sim waveform, it's showing data rate of 16-bit. In HLS window, it is 32-bit, and in 64-bit in hexadecimal. Why?
No, model sim window where 16-bit is it? This one? Okay,
Data
this
rate.
data write. This write data. This one, write data. So write data is actually 64. I have made it hexadecimal.
Okay, fine.
Radix
Right.
I have changed to hexadecimal. So yeah, so because this Avalon interface is actually 64-bit. However, we are using 32-bit interfacing. I mean, we are utilizing 32-bit out of that. So that is why we can control that using the byte enable signal. So if we are using byte enable of 0 1, so that only 1 byte is valid for us. So similarly, if we are using 32-bit, we are I have showed you right in one place we are using 0f. So if you are using all the 64 bits, then it could be ff. So we can control that way. If interface is width is more, we can have control that in byte enable.
Thanks,
Any other questions?
No other questions in the chat.
Okay, so another thing like they can see here, I mean, I saw in this document, you can go through the document also to understand some more details, but I just try to cover them in that session. So here we see that when we execute this function, right, floor square root, we see for every output that the square root is implementing, it is taking a different time duration, or you can say delay, to calculate that square root function. So if you see, like if you have to have argument 4 input is 4 given, then it takes certain amount of time. Okay, in the web form we can check that also. Let's say for example here we give, and let me take one more cursor. So suppose here we got the output, right, somewhere here. So this to this we have a delta of, say for example, 18,000 picosecond. Whereas if you see in the second case, like we are giving the value somewhere here input, and the output is appearing somewhere here. When we are getting the interrupt also, you can check. So this is a duration is increasing, right? So why would we have such increase in the I mean duration is why it increased. So basically it is how we have programmed it. I mean we have designed it. So the functionality we have implemented in that way. That is why we are seeing in this way, right? So if you want to modify something, you observe that you want to modify, you have to basically come here and modify whether this function that you have written, you need to modify that in order to satisfy some of your expectation. You have to come back and modify here, because the way it has been designed, implemented, that is how it is showing in hardware. Okay, so yeah, so yeah, so something like in the quarters, it gives us a summary here, and this we can compare resource utilization wise. We can compare with whatever report we got from the co-simulation. So if you see, they're not exactly equal, LUTs or flip-flops, but they are nearly equal. So initial information we can get from here as approximation, and actual information we can get here from the fitter summary from the quarters. Okay, so let me see if there is anything else I want to show you. Yeah, this we run already, and this report also we opened the HTML report, and we have seen this, and yeah, I think that's all that I wanted to cover and give you a brief about how we can see an HLS IP coming from all the way from C or C++ design coming to this one, like hardware implementation. Okay, so we have come through all the steps, like taking a design from the scratch, then going to the emulation step and checking the functionality correctly, and then we go to the co-simulation step where the IP got converted into HDL IP. The software design gets converted into HDL format, and in HDL format we saw there are reports, there are various folders which is of our use, how effectively we can use with this existing information, and how it has given us a test bench, which is a hardware test bench, and we can see the web form in a hardware simulator like models in here. Okay, so we can do a comparison even on quarters, how much design it takes, and we got all the infrastructure for going ahead with that IP. We can now plug in that IP, which is in a platform solution, design solution, or we can use it as a standalone IP in a standalone kind of system. So there are so many attachment to this particular software code in various ways, and we can basically take out from each domain and start a thread again for a hardware realization. Okay, so these are the basic steps that we covered for in realizing it in terms of HDL IP from a software. So you have any questions on this, please feel free to ask. I will be taking time and answer them for you now. Or if you have any direct questions, do let me know. So that is what from my end.
Thank you so much, Ipsita. There are no questions in the chat.
All right. Yeah, sure. If anything comes up, we'll answer them. So should I go ahead and stop sharing my screen?
Sure, Ipsita. Thank you.
So thank you everyone for this opportunity, and thank you.
Thank you, Ipsita madam. Over to you, Padmanabhan sir. I am made you the presenter now.
Thank you, Biplav. Let me continue. Let me start sharing my screen, and then we will enter into the next section, which is called as RTL versus HLS. So we will first understand then when do we need to go for RTL and when do we need to go for high-level synthesis. Like we have some two simple examples. Let us compare and contrast them. And let us also go through the resource utilization of those examples. And finally conclude in what kind of applications it is better for us to go for RTL and then where we can go for high-level synthesis. And the same square root example, what was written in C++, if we need to develop that in RTL, in Verilog or System Verilog, and we wanted to find the square root of a number, and let us take that design to the Quartus Prime design software and see that how many resources it has taken, and we can just have a quick comparison like what was available earlier and what is happening now, so that we can get into the details. There are two specific labs we are going to take in this session. One is on the state machine stoplight controller, that is based on the basic traffic light controller. So whenever we take a state machine controller or we take a machine where we need to work on the exact number of seconds or clock ticks, right? So then we will definitely have an issue with the controller. That means they are going to work with respect to number of clock cycles. So maintaining them is always a challenge. So let us take the lab one, which is the state machine stoplight controller, where we need to note it down, exact number of seconds tick away before the lights change. And then the lab 2, we are going to take on the parallel multiplies on the incoming data stream, where we are going to multiply pairs of numbers as fast as possible to keep up the data streaming in form of an external DDR. So we wanted to ensure that the multiply operation should be done parallel. So let us take these two examples and what happens in the high-level synthesis and what happens in the RTL. Let us do a small comparison. And at the end of this comparison, let us also go through the Verilog or System Verilog implementation of the similar square root code and see what happens in each and every step. Let us take the traffic light controller. This shows the state machine viewer of the traffic light controller that is captured in the Quartus Prime design software. We have a reset signal, and then we have north-south, and then you have east-west, and all these things. So the state machine is captured. Let us compare what happens when it is written in HLS as well as in the RT. Now the same traffic light controller, which is the high-level synthesis for state machine design, you can see the number of lines of code. It shows 120 lines, and then in the high-level synthesis, you can see there are only 75 lines. The number of registers, we can see in the RTL side, it takes lesser number of registers, but that is not the case in high-level synthesis because of the Avalon slave, so which also takes some registers. And we can also see the bits of memory in the RTL side as well as on the HCL side, both are 0, but then the number of adaptive logic modules, the ALMs, we have only 14 ALMs that are used in the RTL side. But then we can able to see there are more number of RTLs, that means more number of registers, ALMs that are used on the high-level synthesis at the HLS. We can see it is 134. Now we don't use any DSP resources in both examples, even in the RTL side as well as in the high-level synthesis side. And we can also think about the Fmax because we can mention it, the Fmax, and see where we can optimize it. Where Ishita was showing that we can use the synopsis design constraints, right, and we can apply. Yesterday, we have learned in our timing analysis session how to apply the clock constraints and how to apply the input to reg path. That means how to apply set input delay and set output delay. And also we have seen how to constrain the timing exceptions like false paths, multi-cycle paths, and then pure combinational logic delays. So based on the design, whatever constraints you feel that are required for that design, we can approach that and ensure that the design meets the timing what we wanted. What are the key takeaways when we just take the traffic light controller for the HLS implementation? The very important and critical point that need to be highlighted here, you can see there are multiple blocks that are present in the traffic light controller. You can see block 1 dot start, and you can see block 2, block 3. There are multiple blocks that are available there. And why you have more number of loops and then more number of blocks that are available in the HLS implementation? If you have a look at it, you can see that HLS is C or C++ based, which means there is no precise way to specify cycle accurate state machine like Verilog or VHD. So where we have issues is like wherever we wanted to do a kind of traffic light controller architecture where that need to be specified in terms of cycle accurate state machine, because it's a finite state machine. Where we need to specify the cycle accurate state machine, which is very well maintained by the code, which is exactly possible with Verilog and VHDL, because when it is a melee machine or it is a Moore machine, it is easy for us to develop that in terms of HDL by splitting them into sequential logic block, next state combo logic block, and then we can split them into output logic block. That is not the case when we try to do the same algorithm in C or C++, because we don't have that idea, because we cannot split that into a sequential block where we write always a passage of clock and write the sequential block separately, and then we can write another always block for next state combo logic and output logic block where we can split it. So it is very specific, and it is definitely possible to develop a cycle accurate state machine, which we can do with Verilog or VHDL. Whereas as a consequence, when we go through the same with the C or C++ implementation, the traffic light control in the high-level synthesis is only possible with nested loops and if-else or switch statements. So since it is possible with only the nested loops or if-else or switch statements, so it is a definitely tough task for us, because there will be more number of blocks, as I shown in the first session, as Ipsita also showed you. When we click the loops, right, where you can see that there are multiple errors, that means you can see multiple warnings which you can see, where it shows us where it takes more number of initiation interval, it takes more number of clock cycles, and why it takes that information it is provided. And the loops, like which is based on the blocks B1, B2, or B3, B5, and B4, require logic and registers to achieve the desired functionality and best performance. So what we wanted is, while starting the session, what we discussed is our goal is to achieve the same performance like the hand-coded RTL, but with some 10 to 15% or 15 to 20% increase in area, increase in resources. That was the basic idea. But now what happens is, when it is a specific logic where it is a cycle accurate state machine, and that has to be modeled in the high-level synthesis, and that could be possible only with nested loops and a selection of if-else or switch case statements, then definitely it is a quite challenging logic for us. Because of these loops, what happens is, we could see that it requires more number of logic and requires more number of registers in order to achieve the same desired functionality. And also, in order to achieve the best performance, right, it would be a tough task to do that with a high-level synthesis. You can see there are different controls. What is the description here? When you say, whenever you take a block, it takes as an initial control point, whereas the blocks B1, that is B1 and B2, where we need to control the lights, you can see it takes more number of registers. It needs 18 registers to manage the feedback control and the stream IOs as well as and link to other blocks. So there are multiple blocks And each and every block consumes more number of registers in order to perform a specific operation. And in this specific case, we require 50 registers to manage the feedback control, data coherency, as well as it has to perform pipeline. And similarly, on the block 4, we require again 40 registers to manage the feedback control, pipelining, and link to other blocks. So this provides us an idea that when we wanted to implement where it requires a cycle accurate state machine and that need to be done with the high level synthesis, we could see that the blocks are consuming more number of registers to achieve the same set of performance. So when we look back, we can see these loops, like whichever I explained in the slides, the B1, B2, or B3, B5, and B4 require more number of logic and registers to achieve the same desired functionality and the best performance. That is the one which we arrived at for the first lab. Let us explore the logic with respect to the pipelined multiplier, which we need to discuss about. So when we need to go through the pipelined multiplier, where you could see that we wanted to implement 8 32-bit multipliers, which that works at 200 megahertz, where we need to add 4 pipeline stages to meet the Fmax. So now you can see we wanted 8 32-bit words at 400 megahertz and 8 64-bit products at 200 megahertz. Now you can see there is a challenge here. Here it is working at 400 megahertz. And then here you have 200 megahertz. And then again we have 400 megahertz. Now yesterday we discussed more on this clock domain crossing, where we have multiple clock domains. And we also seen that how we can constrain multi-cycle paths. That means if you have 2 flip-flops, one work at one frequency, the other one works at other frequency, how are we going to constrain them? We discussed. Now we can also see there is a PLL where you derive the clock and then you can achieve any kind of frequency. So the max 10 device, you have 4 PLLs, right? So that's what we tried and then checked the logic yesterday. But now if you go through this, we can see that what is our quite challenge is, like you wanted to do 8 32-bit words at 400 megahertz and 4 64-bit words at 400 megahertz that need to be performed. If the same need to be done with RTL. So let us take the sample of the RTL code, where we have the input clock, which is 200 megahertz. And now we use the PLL, right? And then we ensure that there are 3 always blocks, which you could see. The first always block says that always at passage of clock 200 megahertz PLL. And you can see the second always block always at neg edge of clock, which is 200 PLL. You can see this is the passage of clock. And then here we say neg edge of clock. And again, we say always at passage of clock, which is 400 megahertz. So now you could see that we need to ensure that it works on different set of edges. And what is the greatest advantage on the RTL side? And what are the cons, right? The pros and cons when we discuss. What are the other things that we need to definitely take care when we try to do same with the RTL code? When you see the advantages, it is very concise for one specific case. And it is very easy to see parallelism across 2 clock rates and 3 edges in the always blocks. So now you can see there are 2 clock rates. One is at 200. The other one is at 400. And then you can see there are 3 edges. In one place, we say always at passage of clock. In another place, we say always at neg edge of clock. In another place, we say always at passage of clock, which is 400. Now, what are the things that need to be noted down when we have set of multiple clock domains? So when we discuss that for timing analysis, we have to be very careful. There are chances of clock domain crossing. Here we need to figure out the clock domains. And we should also know the exact registers. And we should also know how to pass data across 200 and 400 megahertz clock domain. So that is very, very important for us. Yesterday, we have taken an example of a multi-cycle path where the first flip-flop was driving at 50 megahertz, other was 100 megahertz. So we need to ensure that we require a multi-cycle path constraint to ensure that it requires 2 clock periods to transfer the data from one flip-flop to another flip-flop. We did it for setup, and the same we did for hold by saying n-1, because that is happening on the launch edge. Now, when we say another important thing that need to be addressed here, the specific case is tuned for having the exact number of multipliers. Next question is, what if the number of multipliers was reduced? Now, we need to ensure that all the resources that are utilized in the RTL code need to be taken into account. You can see that how that multiplication and storing in the product register is taken care in the RTL code. What are the quite challenges here? Because we have a 200 megahertz clock domain, and then we also have a 400 megahertz clock domain, and we should ensure that how to pass data across two different clock domains, not only with respect to functionality, we should also ensure that the design should effectively meet time. Another important information is if the same need to be done with the high-level synthesis, which is the HLS code, which we were discussing for the square root component. Exactly, let us take this for a multiplier component. Now, what are the different specific attributes and then the different directives that are available in the high-level synthesis? If you see, we could use the component, and you can also check that there are different unrolling components, like you can see that pragma unroll, and we could see it is like a kind of matrix multiplication. How do we use the normal kind of multiplication with respect to C++ code? So integer I is equal to 0, I less than 16. You can see that I plus equal to 2, and say here J plus plus, and then we can say K plus plus. It is easy for us to write that as a simple multiplication logic in the high-level synthesis code. And when we compare the same, like the number of multipliers, and then what is the kind of loop that we can go till 8. Now, when you compare that with respect to the high-level synthesis, and then we compare the RTL. Now, the RTL versus HLS for the multiplier design, if we compare, the high-level synthesis for parallel multiply exercise shows that it is 8 multiply and 32-bit, but then it could be taken for 4-stage pipeline multiplication, and here you can say that can be taken for 8-stage pipeline, but the number of registers you can see in the RTL side and the number of registers you can see, right? It is more, but then what is very important for us is like, can we achieve the same performance? When you say, yes, we could try to achieve the same kind of performance with the high-level synthesis also, like the way how do we hand code RTL? Exactly the similar case that would be also possible. Now, what is the basic intention here is when we try to write an algorithm, or we wanted to code a specific kind of a compression algorithm, how do we approach the high-level synthesis and how we can write in terms of RTL? So what is the kind of conclusion we arrive at from this table when we say RTL-based method is best for the precise timing, where you have a state machine, and the control-centric operations, where we could definitely go for RTL-based method, because it is very, very easier for us to control the number of resources used and aligning edges to the clock cycles. Because the first example where we utilize the traffic light controller, there was a case where we have multiple blocks, and each and every block was consuming more number of registers. So each and every block, if you see 40 registers, 50 registers, like that. So you can see there are more number of registers that are taken into account because the code uses more number of loops, and each and every loop uses more number of registers. Whereas the high-level design, which we discussed, the high-level synthesis concept, enables the productivity gains for computational centric problems that involve vector arithmetic. And what is the greatest advantage is it introduces the pipelining automatically. And the advantage of high-level design is like it could be good for video processing, AI, and compression application. It is, even though not as optimal for area and performance, but then you can also see you can achieve a quicker development. But then what is very important is you can achieve the similar kind of performance, like what could be possible with the RTL. The same could also be done with the HLS. That's what is shown. So the high-level design is excellent for algorithmic development and analysis, and it is very quick to simulate. That's what we have seen, that like how the code is getting translated into an RTL, and then we also checked, right, each and every step during the lab demo. It is very quick to simulate, and it is easier to create the test benches. And the development iteration cycle improves by 3 to 5 times than the RTL. Now, I will just show you a small example of how the similar kind of logic is written, right? The same square root example is written in Verilog or System Verilog. We have an associated test bench. Let us find out the square root of a number and see that how we can do multiple optimization of the code, and then understand how the same process happens in the high-level synthesis. We can just do an RTL versus HLS comparison. So to get into the details, like I will close this project and then we open. So I say don't save, so it's not required. So let me open the project, the C drive. I have a square root. I will open this PDF file. Okay, let me open the file and explain you the logic. So let us ensure that what kind of parameters and what are the things that we kept in mind while developing the code for any kind of algorithm. So whenever we try to do what are the major important things that we will come up is like we wanted to use the resources. That means we wanted to follow the best practice of the HDL coding guidelines. So what we generally do, we never try to use the block multiplier. We won't try to use directly the division or the percentage symbol because we knew that what kind of hardware it will directly provide. What generally we need to do is like whenever we wanted to perform a set of multiplication or division, we would try to use the shift operators like left shift and right shift, arithmetic left shift and arithmetic right shift operators. So that will provide us an idea of okay how those algorithms could be performed, and it is easy for us to ensure that there can be specific optimization in terms of area. To give you a specific idea about how it has been taken into account, you can see there is a state machine where it is used with the system Verilog enum data type. There are 4 states. You can see init, set, calc, and send. And now, what are the important things that need to be addressed here? The code is written in such a way that it is using only the shift operators, the arithmetic left shift and arithmetic right shift operators, in order to perform the effective logic in terms of the square root. You could see that we use the specific addition and subtraction. Along with that, you could see only the specific arithmetic left shift and right shift operators to perform the process. You can see the arithmetic left shift operation, and then you can see the arithmetic right shift operation that is performed. Then we may need to go through the algorithm, and we should think of okay developing the logic. Definitely, it will be time consuming because we need to go through the algorithm. We should understand that okay, what are the parameters that need to be taken into account, what kind of operators and constructs that need to be kept in mind, and how are we going to develop the logic so that it should take only less number of resources. Number one, it should also meet timing because we wanted this specific design to operate at some frequency, and we wanted that to be timing driven. Because yesterday we were seeing that the design was supposed to work at 100 megahertz. In one case, it was supposed to work at 50 megahertz. It was not working. We need to increase the clock period to 21 nanoseconds, right? So that may be the kind of case which we need to adjust in some specific logic. If you go through the test bench, what we wanted from this is like, we wanted to find the square root of 14, for example. What is very important for us is to understand that, okay, I wanted in the C++ examples we have seen, that we wanted to find the square root of 4, square root of 16, and then 257, 655, 36 like that. Now, if I wanted to find the square root of 14, because it should be in terms of floating point. Now, how accurate I could able to get the value from RTL? That means you can think, because it is our idea, like how do we wanted to optimize and then take it. Definitely, it is tough for us to come up with a test bench where we need to iteratively pass this logic and check whether for after set of successive operations, whether we are able to get the best result. So let us do step by step. First, we will perform analysis and elaboration of this design. Okay, so let us go through the schematic. Okay, now you can see that it is based on a present state and a next state. That means you can able to see there is a state machine involved. We could see the state machine viewer and understand that what are the specific informations that is captured by the state machine. Now, we have targeted for the Maxton device. So let us perform the simulation. So what is very important is let us first perform simulation and see that whether the code is able to produce the result, that is the exact result of square root of 14. So how the process happens, let us find out. So I will remove the title console. Okay, let us perform simulation. Now you can see that it shows in the console, in the transcript, square root of 14 is equal to 119 divided by 1 left shift by 3 bits it shows. That means what we can say is like left shift by 1 bit is like multiply by 2 now. You can say 2 power 5, which is 32. The square root of 14 is nothing but 119 divided by 32. So now what we can try here is like we can check whether it is providing the correct result or not. So just open the calculator app. Now, when we say 119 divided by 32, if we say, it shows that the 3.71875. What was the basic logic is like we could see that, okay, it is, we can get logic like in terms of correct ID also. Now, what is very important for us is like we have to see that what kind of algorithms we are trying to do. And also we should see that whether it is good for AI or kind of video processing applications or compression applications where we have seen what kind of logics where we could use it for the high level synthesis applications. So wherever you require that need to be done in terms of clocks and it is a kind of controller operation, it is always better to go ahead with the RTL because it is in our hands to optimize and then get the approach better. Still, we can synthesize the design. I will close this and we'll continue with the synthesis operation. That means we perform compilation. Okay, fine. Let us try that as a separate logic. Just give me a few minutes. I will just create a project and then I will just open it. right? So let us go through that. Now, if you open the HLS quick start files, where you have the core simulation project, where we have the quarters file. Okay, so once it is done, we can run that logic here. Okay, so meanwhile, what are the other information which we can go through here? It's like whenever we go through the reports, right, we can see the summary report where you can see the estimation, what is taken here. And then we could also compare that with the quarters prime design software. Right, so let it compile the quarters. Let us go through the Intel HLS online training. There are 7 parts of training. I will just show you. You can get through that. If you type in Google Intel HLS online training, it takes you to the introduction to high-level synthesis, where you can see a 65 minutes online training course, where you can also see the specific lab that you can do. So this is the part 1 of the high-level synthesis training. So this is like this, you can have 7 parts of the training. If you have completed the first part, you can go on continue the rest of the course. Stop sharing. If there are any questions, please let me know. Are there any questions in the chat? I couldn't see anything.
No, I don't see any new questions.
Okay. All right. So now we can see the reports. So final reports, I will again show what Fpga has shown the similar logic. You can see that it shows 2003 logic elements. And then you can also see 1805 registers. And we could see that whether it uses any specific component with respect to state machine. Right, so you could see that it doesn't use any state machine. Whereas when we develop the code, then it is a kind of a state machine logic, because it is a cycle accurate machine, and we could try to do that. Right, so let us summarize what we have seen. Let me go to the first session. Right, so what are the 3 objectives? Like we have to see, like we understood the concept of high-level synthesis for Intel FPGAs through a demo. We will have the hands-on session in the afternoon where I will explain you about the NIAS, as well as we can do the HLS lab. We can use the Intel HLS compiler to synthesize, functionally verify, and simulate the design. And we could also understand how the component executes on the FPGA. Okay, so I will share the square root code of the RTL along with the test bench. You can simulate it, and then you continue with the compilation process. And you compare both with how many resources are taken in the RTL versus HLS. There are a few more minutes. I hope there's some question in the chat. Okay, so right, yes, it will be shared in the Google Drive after the afternoon session. After 1:30 to 2:30, I will explain about the NIAS and the other components. Then it will be shared in the Google Drive. Meanwhile, you can also install the Visual Studio 2010. So, Ipsita, can we show that to them so that they can get the link and start installing it before 2:30?
Okay, let me just get back and check the link.
All right, otherwise I will also check from my side.
Yeah.
So this is the link which we will share now. You can see that it shows Visual Studio 2010. This is what we want. Okay, so don't download the language pack. So download Visual Studio Professional 2010. You can download the DVD, and then you can run the setup file. It will automatically install Visual Studio 2010, what we showed in the demo. So this link would be shared with you. I will put it in the chat also. You can create your login, and then you can download the Visual Studio 2010 before our lab. The same link is also shared with you in our schedule. You can also check that once again. Okay, if there are no questions, over to Biplav.
Thank you, Padmanabhan sir, for such a nice session. So now we can wind up the first half of the session. So we will again rejoin at 1:30 p.m. sharp. Please be on time, dear participants. Thank you, everyone.
Thanks, everyone. Let us meet by 1:30.
Good afternoon, everyone. Welcome to the post-lunch session. So this session will be taken by Mr. Padmanabhan Kalyanaraman sir. So this session will be taken by Mr. Padmanabhan Kalyanaraman sir. Sir, are you there? Padmanabhan sir, are you there? Am I audible?
Shall we start or shall we wait for a minute?
Yes, sir. Yes, sir. Sir, I request you to please start with the session. Over to you, sir.
Thank you so much. Yeah, I'll start the session. Right. Good afternoon, everyone. Welcome to the quarters integration and system integration session. Before getting into the details of that session, let us first get introduced to the intellectual property, which is called as an IP catalog. So after we get some idea about the intellectual property about the IP catalog, then let us move on to the NIAS, which is the soft core processor, and then we can develop a NIAS soft core based embedded system design. How to create, I will just show you an example. There is a specific lab based on that, which I will explain that to you, and you can complete the hardware design successfully. Complex functions that Intel designs for our customers, so they don't have to design it themselves. That's what we call that as an intellectual property. Sometimes IP is free. The more complex stuff it costs, since it is very expensive to develop and make sure it works. So what is very important for us is when it is an IP, the intellectual property can be what, when you say they are pre-designed, they are pre-tested, and then they are pre-verified. So we can directly integrate that to the system and perform a specific set of tasks. So we don't want to develop anything from scratch because the Ethernet controller is already available. We don't want to design any control. Similarly, there is a PCI Express controller and the soft core processor, which we are going to discuss in detail today. And then there are multiplayer functions, some basic functions are also available. Where is the IP catalog when you say? It is a centralized tool for the implementation, configuration, and generation of IP cores that are optimized for a specific device family. So if you open the Quartus Prime design software, we can see on the right-hand side, there is an intellectual property, which is called as an IP catalog. Let me walk you through that. I'll close the design. Let us create a new project. Say next. And in the C drive, I create an IP design. Okay, and then integration. So let us give the name as memory, or you can say mem. Okay, or you can say RAM. So we can say memory we can take RAM 32 cross 4. So what is the name of this project? Is RAM 32x4. And in the C drive, we have created IP design integration. Let us say next. Say create it. And let it be empty project. And we say next. Add files. We don't want to add any files here. And we can target the device here. Max 10 devices. So 10M50 DAF 484C7G. Now select the device. Say next. There is nothing to specify in the EDA tool settings. And say finish. So in the IP catalog, on the right hand side, you can see basic functions, DSP, interface protocols, memory interfaces and controllers, processors and peripherals, all are available here. There are some university program IPs also available. Let us start with the memory because our memory is RAM 32x4. That's what we wanted to design. What we need to type here is in the IP catalog, we have to type here on-chip memory. The moment we type on-chip memory, you can see all the memory components are listed on the right hand side. You can see T4, it is first in, first out, RAM single port, RAM 2-port, dual port RAM, and single port ROM as well as dual port ROM. All are available here. What is very important for us is like we need to develop the memory. How are we going to do that when you say? We need to say RAM single port. We can click that. And the moment you click RAM single port, it shows that we need to provide the IP variation file name. Okay, so IP variation file name is the name what we have created here. What is the name of the module? Just you can type here RAM 32x4. Here you can get that in terms of Hdl or you can also get in terms of variation. Let us say OK here. So this is called as the Mega Wizard plugin manager. So in the Mega Wizard plugin manager, you can see how wide the Q output must be. You can see and how many 8-bit words of memory. All this information, sir. Now you can see on the left hand side, there is a data which is 7 down to 0, write enable, address 7 down to 0, and then clock is there. But what we wanted is 32x4. So we should change these bits to 4. And how many 4 words of memory you should change this to 32. What is the memory we wanted is 32x4. That is the memory which we wanted. And now what is the memory block type B? When you say, you can see that it can be auto or it can be MLAB. MLAB stands for memory logic array block. That's what I explained to you, which is called as a distributed memory. And then you also have M9K. That M9K is the memory which is present in the max 10 devices. So you can say the resource usage, you can see 1 M9K. Okay, so now if you give auto, the tool will try to select the resource, best resource, right? So in our case, we wanted a memory which is 32x4 we have provided. And we can select either M9K or you can let it be auto, whatever may be the scenario. But the moment when you click auto also, it shows the resource usage is 1 M9K. That's what it is going to take. Now what is important here is like if you see the signal clock, that is connected to a register. You can see the output and then the Q is also registered, right? And then it goes out. Now you wanted the Q output to be registered, then we can have this flip-flop. If you don't want, then we can make that as a wire where we could use a continuous assignment statement. So what kind of clocking method would you like to use? Is a single clock. We say next. Which ports should be registered? Now you say which port should be registered. If you want the Q output to be registered, then we can check it because it is already checked. If you don't want the Q output to be registered, we can uncheck it. Now it becomes a wire. Now what are the other informations that are available in the IP catalog when you say? We can create the enable signal, the clock enable signal. We can also create an asynchronous clear signal. So all these signals are already available. If you wanted, we can add this clock enabled signal and asynchronous clear signal and read enabled signal, everything to the memory if we wanted. Otherwise, we can go ahead with data, write enable, address, and the clock pin. If you want any other extra signals that need to be added, we can add that here. Say next. Now, this option is important for us to see that what should be the Q output be when reading from a memory location being written into. That means if read and write operations are happening at the same time, to avoid memory collision, right? Whether it has to take the new data or it has to take the old data or it has to take X. That's what is specified here, either new data or old data or don't care. So we can click here new data and we can say next. Okay. Right. Here there are two important things that need to be addressed. One is, do you want to specify the initial content of the memory? When you wanted to specify the initial content of the memory, we should say, yes, we wanted to specify because it is a memory initialization file, which is called as a MIF file. If you don't want to create it, we can just say no, leave it blank. In this example, just I will say no, leave it blank. And in another example, I will show you how to create a memory initialization file, and that could be integrated. So now we can say no, leave it blank and say next. Okay. And we can generate the netlist, say next, and you can get the instantiation template file and say finish. The moment we click this, you may get a dialog box stating that whenever you create an Intel IP variation, a Quartus prime IP file will be generated. This is called as the QIP file that is generated. And the Quartus prime IP files are used to represent the Intel IP in your design, which is the Intel IP we are using in the design that we can see. Do you want this IP to be added to your Quartus prime project? When you say, you should say yes, so that it will automatically add. Now you can see in the files tab that the QIP file is there, and then you can see the very log. Input 4 down to 0 address, input clock, input 3 down to 0 data, and input write. Now automatically we can perform analysis and elaboration. Now in the first case, we develop the memory code. Second case, we use the insert template to get the memory code. Now third case, we don't want to do that. We can get the memory from the IP catalog. Okay, now you can go to tools, go to the netlist viewers and say RTL. Now you can see there is a memory component, the RAM block. So to get that in the specific details, what kind of memory is used, we can perform compilation of the design. Now you can see the total number of registers, nothing is there, but then you can see memory bits. 32 cross 4, which gives you 128. Okay, now you can see how many number of PLLs are there because it is a max 10 device. There are 4 PLLs. Okay, and the maximum frequency what it can operate is up to 473 megahertz. Right, now you can see what are the informations that need to be noted down here is like we need to perform the synthesis process and the implementation process. We did it. Now we need to go through the technology map viewer post fitting. So when we expand it, you can see that it's a RAM block. Now at the end of the fitter operation, we can see that what resources it used. You can see this is a RAM block, which is a block RAM. To get more details, we can expand the filter operation, go to the resource section, click resource usage summary, and here we can see that M9K blocks. It is using one M9K block RAM memory. That's what is used. Out of 182 M9K blocks that are available in the Max10 device, your code has used one M9K block. So this information, we can see it in the resource usage summary. In this case, what we did is we didn't write the Verilog code for memory. We didn't copy paste the insertion template. We directly have taken the on-chip memory from the IP catalog, which is called as the intellectual property catalog. We synthesized and implemented the design, and we have also seen that what resources it has. Okay, right. Now, what is another important thing which we can also try with the memory that is important for us in order to get into the system level? Till now, we were working on the block. Now, what is the meaning of that entering into the memory initialization file logic? Let us see that. We wanted to initialize the contents of the memory. How do we initialize the contents of the memory? When you wanted to initialize the memory contents, we can do from here. So file, new. Here you can see that memory initialization file. Okay, it can be either .htx file or it can be a .mif file. The .mif file is the memory initialization file. We can say okay. Automatically, what will happen is it will say 256 cross 8. Because the number of words and word size both are there now. Now, if you click OK, it is going to create a memory. You can see that starting from 0 till 255, all the locations are filled with 0. If you don't want these memory contents to be filled with zeros, what we can do is we can say right click and say custom fill cells. When we say custom fill cells, it is asking you what is the starting address you want and what is the ending address you provide. So I say that it should start from 0 and then it should end at 255. Okay. So then what we can do is like we can perform incrementing or decrementing. Right? You can say either incrementing or decrementing and say that I wanted to start value. So starting value is 0 and I say that increment by 1. What I have entered here. The current address radix is unsigned decimal. The starting address is 0, I say, and ending address is 255. And you start at 0 and increment it by 1. So you can see here, increment or decrement, both are there. So I say increment it by 1 and say, okay, now you can see that the entire file is ready right now. The memory contents is ready now. 0, 1, 2, 3, 4, 5, 6, 7. And then it goes till 255. Now you can say the contents of the file. So file and say save as, and you can save wherever you want. For example, the name of the file, whichever you wanted, you can save it. The memory initialization file will also be added in your. What are the two options here? One, while creating the intellectual property IP, we don't want to say to the tool that you have to include this memory initialization file. So in that case, we can say no, leave it blank. When we wanted to tell the tool, yes, you include this memory initialization file, then what we are trying to tell the tool is use this .mif file. So in that case, we can create a memory initialization file. And while creating the IP in the MegaWizard plugin manager, we can tell the tool where the memory initialization file is available located, and we can tell the tool to include it. So that is also possible. Right. So these two are on the block level. Now, how are we going to create in terms of system level? That means how do we create all the components in the platform design? That's what we are going to understand. Before getting into the details of the platform designer, we need to know about what is a hardcore processor, what is a softcore processor, and what is the meaning of the embedded system with a softcore processor. So to get into that, first I can show you some important details like what is present in the IP catalog. Okay, so I have showed you the information. Let us start from here. What we did is we need to create a memory editor. It can be either .hex format or it can be a .mif format. What we did is we opened the memory initialization file, or you can select the Intel format, which is hexadecimal file. It is showing that number of words and word size. Then you can provide the memory space editor options, whether you wanted that to be having how many cell size you wanted in a row. That also we can constrain. You can see cells per row. By default, it is showing 8, but you wanted to change that to 16. That is also possible. Now it is showing that 16 cells per row. Then we can say custom fill cells. That's what I did. And you can say starting address 0 and ending address, whichever you want. I gave in our case 255, and we can say OK. Like this, we can generate. Okay, once it is generated, then what to do when you say, while creating the IP, while designing the IP in the platform, in the parameter editor, where in the MegaWizard plugin manager, there was a place where no leave it blank. In that case, you can say yes, use this memory file, and you can provide that. It can be either .hex file or it can be a .mp. So this is the way how we can integrate the memory into the design. Also, you can include the memory initialization files into the design. Okay, so this is very important for us. The second thing what we need to understand is called as the platform design. I will give some basic introduction about that, and then we will try to create a system, and I will show you a simple lab on that. So in the platform designer, what is exactly a platform design? Let us understand. We need to do a system design entry with the platform design. So what exactly is a platform designer? If you say, it simplifies the complex system development because it generates the system automatically. It raises the level of design abstraction, and it provides a standard platform. That means IP integration, custom IP authoring, as well as IP verification. It enables the design reuse, and it scales easily to meet the needs of the end product. So what is the greatest advantage is it reduces time to market. That means it reduces the design development time, and it eases verification. So now, why do we require this platform designer? When you say, in our system, there may be multiple components that need to be connected here. For example, you have a processor, and then you have a PCI Express. Both are master. And then you can see there are multiple slave devices that are connected to it. We need to communicate between the master and the slave. For that, we require a bus interface. And what is the bus interface that is used in the platform designer? That's what we are going to understand. And the typical system uses, that means it requires significant engineering work to design custom interface logic. And we also need to know integrating the design blocks and intellectual property is very tedious and error. That means if you want to integrate multiple IPs and then you need to develop a system, it is very, very tough, right? And you cannot do that manually. But how are we going to solve this problem? Is with the help of a platform design. What is the advantage of that? When you say it avoids error-prone integration, it saves development time with automatic logic and HDL generation, and it enables you to focus on value add blocks. And platform designer improves productivity by automatically generating the system interconnect logic. So it helps you to completely do that. Right? So we wanted to perform the automatic interconnect, then we can use the platform design. How the platform designer GUI will look like. In the morning, I showed you a simple glimpse. Now we can get into the details of step by step we can do now. So if you see the platform designer GUI, it has an IP catalog. On the left-hand side, you have the hierarchy, you have the system contents, and then you have messages. They all are available here. Right? So what exactly would be there in the platform designer resources? So these are some of the trainings which I can share it with you later. Let us get into the details of how we create an embedded system using the platform design. You can see there are multiple online training courses, right, which will help you to learn more about the platform design. Okay, so I will share this with you. You can practice that and then get into the details. Right. So there are 3 more slides which I need to explain to you right now. And our focus would be on the soft core processor today. But on Wednesday, we will discuss more on the hardcore processor, which is called as an SoC FPGAs. Now, processors in SoC FPGA can be either hard or soft. That means what is hard, what is soft. Let us understand that in detail, and then we will enter into the SoC FPGAs in detail later. When you say hardcore processor, they are implemented in the fixed silicon logic of the SoC FPGA, similar to serial transceivers. That means they are dedicated silicon, which is immersed on the FPGA fabric. Along with the FPGA, you also have a processor. That means the Cyclone 5 device uses a dual-core ARM Cortex-A9 processor along with the FPGA fabric. So what is the advantage of having a hardcore processor when you say? The hardcore processors offer higher CPU performance than soft-core processors. And depending upon the factors such as processor architecture, clock rate, and process technology, etc. Means you can operate up to 1.5 gigahertz when I say. That means it gives you higher performance. The same cannot be achieved with the soft core processor. Why? That we will understand right now. Now, the hardcore processors are available in our Agilex devices, Statix devices, ARIA devices, and Cyclone 5 devices. So the hardcore processor is not available in our Max 10 device because which is having only the soft core processor. Now, what we need to understand is what is a soft core processor, because we are going to create an embedded system design now using a NIAS2 processor, which is a soft core processor. The soft processors such as NIAS2 are implemented in programmable logic. That means the NIAS2 processors are going to use the FPGA resources. It is going to show us like how many lookup tables, how much memory, and how many DSP resources are used. That can be present in the soft core processor. And the advantage of soft core processor is like you don't require a dedicated silicon because it is going to use the resources which are present inside the FPGA. But what is the only drawback we will have when you say? The drawback is the performance and the cost are typically lower than in terms of hardcore processors. That's what we have to take into account. Even though we have to see that you don't require a dedicated processor that is immersed inside the fabric, the performance and cost are typically lower. And what is the advantage of NIAS2 processor? Benefits when you say it is a scalable performance. It is available in all the FPGAs like multiple CPU, custom instructions, hardware accelerators, and from concept to system in minutes. So it works with all Intel FPGA devices. Okay. Now, when you say FPGA-based embedded system design, you can see that why do you wanted to have FPGAs for embedded system? Because it has memory controllers, GPIO, UART, everything. And we can also do co-processing, which is an important task. And we can do custom embedded controller operation as well as the multiprocessor application. The many important thing is like here, whenever we do signal processing or image processing or packet processing applications, we use the FPGA as a co-processing device. Right. So this is important for us. And let us go on to create the NIAS2 processor-based embedded system design. Okay. So I will just show you one small example. So create a new project with that. Soft processor embedded system. Okay, what is the name of the project? Test it out. Create it. We can go to the tools and we can open the platform designer. So now in the left hand side, we can start typing the processor. It's an embedded system. You start with a NIAS, which is a soft core processor. So the soft core processor is available in two variants. One is called as the economy variant, and the other one is called as the fast. Economy and fast. Now, when it is an economy variant, okay, so that means you can see that it is JTAG and ECC only RAM protection, only small features are available. Whereas when it is a fast variant, you can have more number of features. Let us start with economy variant. We don't want to do anything much right now. And say finish. What is important here is like you have a top level signal. And then we have taken a processor. Now what I wanted is I wanted to take the processor, I wanted to take the memory, and I wanted to take some UART, some peripheral, and I wanted to connect them in the system. So how do we need to do that here when you say it? Now you can see that. What is the interface? Let us check out. What are the errors you can see here? NIAS to clock need to be connected to a clock, and reset must be connected to a reset source. Now you can see that there is a clock source, right? You open that, directly that clock will be connected. And then you click reset source, then reset will also be connected. So clock, reset. Now, let me take one more device, which is called as an on-chip memory. Because when there is a master, we require a slave device. We use this on-chip memory as a slave device. Double click that. And if you want dual port access, then you should say click here. If you wanted to have only the single port access, we can make it. So now you can see that why did we discuss about memory initialization, all those things. If you wanted to initialize the memory content here, then it will ask you for the memory initialization file here. Now I have unchecked it, then it shows that this memory is not initialized during device program. We don't want to initialize the memory content. What is very important here is the slave data bit, because your NIAS to soft core processor is a 32-bit embedded RISC processor. And the slave bit, what I am selecting for the memory is also 32-bit, so that it is compatible to it and I can connect this memory as a slave. So say finish. Now what it is showing is what is the interface between the processor and the memory. If you see here, you can see Avalon memory mapped slave and Avalon memory mapped master. So this is the interface which is used in Intel for connecting the devices. Now, first thing is we need to connect the clock and the reset for the on-chip memory also. So you connect the clock and you connect the reset. Now what we need to do is we also need to connect and ensure that the slave device is connected to the master. So connect the slave, right, to the instruction master and the slave device to the data master. The instruction master and data master are connected to the slave device. Okay, now let me take one more device called as an UART, data UART. Just connect. Even that UART, if you wanted to connect, we need to click the open dot where clock will be connected to the clock. Reset will also be connected. Now this Avalon JTAG slave need to be connected to the master. Connect that also. And if you wanted to have this interrupt connected, we can connect that processor interrupt to the peripheral interrupt. We can connect that. Now you can see there are multiple errors. So we need to rectify these errors before generating the HD. Okay, how do we need to do? Let me explain that to you right now. Now, the logic is you can see the addresses are getting overlapped. Now, since the addresses are getting overlapped, now what is very important for us is like we wanted to tell the tool that you map the address, or otherwise we have to do it manually. You can see that the addresses are same, like 0FF. So it is a problem for us to proceed. So what we can do is we can tell the tool system and say assign base address, so that it can assign the base address. The addresses are modified. Now there are only two errors which we have. One error is it shows that a reset slave is not specified. Please select reset slave. And exception slave is not specified. Please select the exception slave instead. That means we need to tell to the tool that the on-chip memory will work as a slave for the NIAS2 processor. How are we going to tell that? We double-click this NIAS2 and we expand this vectors tab and see there in the reset vector memory, select the on-chip memory. Similarly, in the exception vector memory, select on-chip so that you can see the errors are removed. Now we can generate the HDL. When you click generate HDL, it will ask for the synthesis files as well as the simulation files. The synthesis files will be used for compiling the system into the Quartus project, and the simulation files will be useful for creating a simulation model in the simulator. So just to say generate. And you can give any name whatever you want. For example, I give this as a test, okay, .qsys, which is a platform designer system file, which is a .qsys extension. You can say save. And say close. Okay, now you can say close. Right, now what we can do is like, we can minimize this platform designer, come to the Quartus Prime design software, and then we can add the files here. Okay. In the project tab, click here, add or remove files in. In this case, what you can say, there are three dots there. Just click that. And then you can add the QSys file, test.qsys. Just say open, apply OK. Now, if you go to the file, you can see that the test.qsys is also added to the Quartus Prime design software. This is the way how you can perform the system, right? You can develop the system in the platform designer and take it back to the Quartus Prime design software. Integrate that in the Quartus Prime design software. That's what we call that as a system integration. You need to integrate that to the system. So we took a memory, we took a processor, and then we need to take it to the Quartus. Right. So based on this, there is a small lab that is available to us. I can show that lab manual to you, and you don't need to go to implementation. You can stop till compilation, because if you don't have the board, there is no point in generating the SRAM object file and implementing on the board. What I suggest is you can complete the hardware design. I will explain what is possible from your side right now. So embedded FPGA design with the NIAS2 processor, which is a shortened edition. So shortened edition means you have multiple connections which are already there. You need to connect only minimal connections. That's what we are going to do right now. Okay, so what is this design? As Ipsita explained in the morning, this design is based on the NIAS2 software, where we are going to connect all these components: NIAS2 soft core processor, on-chip memory, JTAG UART, switches, buttons, LEDs, 7-segment display. Now, in this, all the other components are already connected in the platform designer system, and you need to connect only the JTAG UART. And we are going to complete the hardware design. This is the lab which we are going to do now, right? I will share the lab manual, as well as I will share the lab files with you. This will give you a clear idea of how to create the system, embedded system. So you don't need to enter into the software design, because when you enter into the software design, you may need to implement the design onto the board, because you need to use the USB blaster and you need to implement the design onto the board. So since you don't have the board, I request you to complete the entire hardware design, which I will show you right now. I request you to complete that portion, right? That is one, along with the HLS lab, so that you will get an idea of system level, as well as you take one block and integrate that to the system. So both you will be comfortable, right? So let me start this design. Where are the design files? How do you start it? I will explain now. The design files will be already there in the folder which I will provide you. Okay, so you don't need to worry anything. Just copy the design files from here. Go to C drive and say embedded lab and say IITG. Now inside that embedded lab folder, you paste design files. Inside design files, you can see all the files are available. And what we are going to open is the DE10 Lite QSys semi-completed .qar. It is the Quartus archive file which is semi-completed, not fully completed. And what we wanted to do is we need to complete it and perform the hardware design. That's our target right now. So this is a generic example, but then what I'm going to show in the lab manual is a specific example. Let us try that now. I will close all the quarters now, and let us start that example. So go to open project and open the C drive, embedded, okay, lab IIT3 design files. Inside that, D10 Lite uses semi-completed .quartus archive file. Just open that. Okay, right. Now you can see there is a top.v file. This is our file. What is this is, you can see that this particular DE10 Lite has 6 hexadecimal displays, 2 keys, 10 LEDs, and 10 switches. All are available here. That's a top module. Okay, after reaching this place, directly go to tools and open the platform design. Okay, once you open the platform designer, you can see that NIAS2 setup version 2.qsys. Just click the qsys file and say open. You have to wait for a minute so that it will load the entire design. You have the CPU, which is nothing but the NIAS, on-chip memory, button, LED, switch, hexadecimal 0, 1, 2, 3, 4, 5. All parallel input-output components, memory, CPU, button, everything is there. Now what we need to do is like, there is one specific connection which is missed now. That means we are going to add one UART. So in the lab manual, to open lab 1, building your platform designer based processor system. That's what. Now in this, we already have opened the QSys file. Now we are going to add the last remaining component, which is called as JTAG UART. So in the IP catalog, type here JTAG UART. When you double click that, this will take you the JTAG. Now, as discussed in the earlier demo, it is our responsibility to connect the clock, to connect the reset, to connect the Avalon JTAG slave, as well as the interrupt. Everything when you connect, you could see that there is a set of errors which shows that it is overlapping in terms of the address. So all the addresses are getting over. How are we going to sort out that issue? Go to system and say assign base address. When we do that, you are not getting any errors. Okay, so this is the only one step you are going to do in the lab. Okay, search the JTAG. Do JTAG you want, click and add that, and you connect all the system components together. I have connected all the components. If you have any doubt, you can try that one by one by following the lab. Once you do everything, you could see that there are some errors which are coming in terms of the base address. So you have to generate the base address. So you need to just click system, assign base addresses, and say file save, and then you can generate the HDL, click generate, finish it. That's all. This is exactly the same demo which I showed you earlier, but to get the practice, right, I will share you this lab manual as well as the lab files. Please complete the hardware design. Okay. Now go to yes, file, save. Okay. Once the file gets saved, click generate HDL and say generate. Okay, now you say close. If you go through the lab manual, what steps we have completed? Generate HDL over, click generate over, finish. Now, once we do this, we need to come to the top level. We are going to complete Quartus Prime Design software compilation. Because what is important here is you have the JTAG that need to be connected to the board, and you have the CPU, then you have the LEDs, hexadecimal displays, everything. Now, what we wanted is we should open the top module. That's what I opened and showed you. This is for the D10 light. And we need to perform synthesis. That means we need to add the IP, which is the QIP file, which is generated from the platform design. Okay. So how do we add it? I will show you. So go to the Quartus, go to project, add or remove files in project, and click 3 dots. And inside that, you go to NIOS setup V2. Inside that, there would be a folder called synthesis. Double click that. You will be getting a QIP file, which is the Quartus IP file. Add that IP file, which has been generated from the platform designer. Apply, then OK. That's what is explained in this place. Okay, once we do this, what is our thought process is, we need to check whether the pin numbers are correctly given for the LEDs, hexadecimal displays, everything. So to cross verify that, we should open the assignment editor. So go to assignments and click assignment editor. When we click assignment editor, this is for Max 10 device. You can see how you can easily recognize, I will tell you. Just to go through the LEDs, because from the example, right, we are through with like the LEDs, like you can see there are 10 LEDs, and you can recollect for the first lab, we did LED R of 0. In that we gave pin underscore A8. So these are the IO standard values, and these are the pin numbers for all the LEDs. Similarly, these are the IO standard values for all the switches, and these are the locations of all the switches. Everything is there. Along with that, you have VGA, you have memory, you have G sensor, Arduino, all are available in the D10 Nano. Sorry, D10 Lite. But you don't need to worry about all those things right now. So just see whether all the informations are correct here. Then we can continue with the compilation. What is the last step here is we can perform compilation. So you can complete till here. Congratulations. Your FPGA hardware design is now complete. Okay, we can do till that place. So you can go to the Quartus and click compilation. So once it gets compiled, then I will show you what is the specific logic and what are the informations that need to be checked out in the design. Okay, let it do that. Meanwhile, I can also explain you that there is another way of approaching this. In this lab, what we did is only the JTAG UART you connected. But that may not be the case always, right? We may need to understand and then do it from scratch if you wanted to try that. Yes, so I have one more lab manual, which I will share it with you. I request you to try that also if you have time, right? I have an embedded long lab. The meaning is, in this embedded long lab, we are not going to start directly from JTAG. So how the lab will get started is, you have to start from connecting the processor. We are going to connect one by one. Okay, so don't worry about the board implementation. Start from here. Connect the NIAS2 processor, memory. Then you are going to add on-chip memory. After adding on-chip memory, JTAG UART. Then one by one, you can add all the parallel push buttons, switches, LEDs, hexadecimal displays. One by one, you have to do step by step. And after performing all these connections, you have to generate the HDL, system base address. Then you generate the HDL, click finish, and you build the top. And you can complete the top. So both labs are available. In this lab, which is the embedded long lab, you have to start from NIAS and then you should end at the hardware design. Whereas in the embedded short lab, already there is a semi-completed QAR file in which you need to just add only JTAG UART and complete. So I will share both in the drive, but I request you to try the long lab because that will give you an idea how to create a platform designer system. But if you wanted to just check what is happening in the hardware design, you can try that with the embedded short lab. Is there any questions in the chat? Okay, all right. Let me open the purchase now. It was 100%. You can see how many number of resources it is taking and how many pins, all these information are available. Okay, if it is having any FSM, then we can see, is it a state machine viewer? You can see there is a state machine. And here you can see that what is the source state, what is the destination state, at what condition it jumps from one state to another state. Okay, so the first lab, what you need to do is the NIAS lab, both long and short, both I will provide you. Try that. If you have installed the Visual Studio, then you can try the HLS lab also. I can just show you a quick demo before you start the lab. I will close this. Okay. So I'll stop sharing and then I will open the HLS lab and then I'll continue. So what we are going to do in this lab, I will explain that to you right now. If you open the HLS quick start files, you can see there is a commands.txt and floor square root.cpp, and you can also see the HLS lab. What was explained in the morning is you have to first change this, okay, the setup.txt to setup.bat, okay, and then you have to do the lab. Okay, let us start from scratch now. In the earlier example, we had everything, but in this example, we have only these three. So any device you can connect. So open the Visual Studio. So in the command prompt, at the start, I am just typing that. So here, you need to come to this drive first. So now this is my user. So inside this, you have a setup.batch file. That's what we are going to run now. Okay. So run this setup.batch. Now, once we do the setup.batch, what we are supposed to do, there are two steps we need to do. Okay. One step is we have to perform the Hls emulation. The second one is called as co-simulation. First, on the software side, we are checking. Then on the hardware side, we are checking. First, we will check on the software side. Copy this. Okay, now what we can say, emulation dot exe util. You can see floor square root of 4 is 2, 36 is 6, 257 is 16, 65536 is 256. Now what we need to do, we have to try the second option, which is our Hdl. This is what is explained in the morning. I'll just give you a quick recap. So run that. And we are targeting is for the max step. As Ipsita explained, it will take 2-3 minutes for us because it is going to generate, okay, in terms of FPGA, how many lookup tables and how much memory, how many DSP resources, all those things it is going to generate. So it will take some time for us to get the report. And you will be getting a compilation report where we can get the details. So you can say co-simulation dot exe, you can say. You can see that. On the software side also, the HLS component, the values are correct. And we have seen that on the FPGA side. Now what we can do, we can minimize this. Okay, and then we can go to the HLS quick start files in our downloads folder. Open that. You can see the co-simulation.prg folder. There you go to reports and then open reports.htm. You can see that Monday, March 14th, 1428. Now we have generated the build. You can see how many lookup tables, how many flip-flops, how many RAMs, and how many DSP blocks that are available. Not only that, you can also see that each and every loop, as I mentioned, right? Each and every block. See, this is line number 16. When you say line number 16, it starts the specific block. And you can see line number 28. Okay, here you can see that if all the blocks, wherever you have if loop and then while loop, everything will definitely consume more number of clock cycles that we can see it. So these information, I request you to go through all these things. That's what our HLS. Do you have any doubts? I will share the lab manual in the Google Drive, and I request you to go through both labs. And if you have any doubts, will be available, and I will help you out. Okay. First, complete the embedded lab, then you can complete the HLS lab. Okay. Both I will put that in the Google Drive, and I will also share the HLS slides for you. And you can refer that because you have the multiple choice test today. So go through that in detail.
Very good afternoon, everyone. So dear participants, today we are having one MCQ 1 at 4:30 p.m. It will be of 25 questions and it will be of 30 minutes duration. So all participants are requested to attempt the MCQ at the allotted time. The link has already been shared with you in the Google Drive. You can find the class drive which was shared with you in the registration confirmation mail. Here you have a link of the Google Drive where all the documents and class materials has been also shared with you. An announcement page is also made there where you will find all the necessary links and also the class materials and reference materials for last 3 days has already been shared with you in the Google Drive in revised version. You can find here also. In case of any queries, you can just write in the chat box. Thank you, everyone.
Thank you, Biplav, for your announcement.
Welcome, sir. Dear participants, we will be sharing the link in the Google Drive. You can check the Drive link in the registration confirmation mail. Also, I will share it in the chat box. You can just copy the link.
Right. There was a question in the chat regarding the square root example. So if you see here, in the morning I explained you about the square root. If you go through the files, you have square root.sv, and then we have seen the test bench also. Okay. Now the idea is, if you go through the compilation report, it shows the total number of logic elements are very less, like it is only 288, and total number of registers is also 67 only. We are not getting more registers like what we got in the HLS example. When we open the HLS Quartus compile.qpf file and then you compile it, and then you try to develop your own Verilog code and then verify it, right? So then you can see there is a fundamental difference. Okay, so now you can see that it takes only 288 logic elements and takes only 67 registers. So if you go through the netlist viewers, you can see that. Okay. Also, we can note out the state machine. So tools, netlist viewers, and then you can go to the state machine viewer. You can see there is a state machine. Init, set, calculate, and send. And you can see the source state, destination state, as well as the condition. Okay. I will share this square root.sv and square root tb.sv in the Google Drive, in the shared folder. Please try that also. That will give you a good idea on how this will work out for a RTL design. You can practice that also. Okay. I hope that answered your question, but please go through that. You need to try RTL viewer, technology map viewer post mapping, technology map viewer post fitting, state machine viewer, and also you try to see the simulation tool, where you can simulate the design and find the square root of 14, because that is the number I have used in the design. You can also try that. You can give some other number and check whether it is finding the square root also for that. I will share this system Verilog code and the test bench with you. You can try that.
Dear participants, all the links for the YouTube live sessions is available in the Google Drive. Please check the drive, you will find there.